Hi there, I'm Tucker Balch. I'm a professor at Georgia Tech, and I'm the instructor for this course.
Hi, I'm Dev Priyadave, a graduate student at Georgia Tech. You can call me Dave.
My original research was about machine learning for robotics, but in 2007 I became interested in using these same algorithms for investing. Since that time, I've shifted my research and teaching towards finance. I also co-founded a financial technology company called Lucena Research.
I'm a graduate student who's been working with Professor to build a predictive system for stock market. I'm also working on the software to support this course.
You're going to see a lot of Dave in this course. She makes a lot of things happen behind the scenes. Now, Dave, I'm thinking about buying Apple stock. Do you think I should do it?
Well, it depends on a lot of factors. What are the other stocks in your portfolio? What do you think will predict stock prices? Also, how much risk do you think you can take it on?
So those are all good questions, and Dave is exactly right. We need to consider all of those things before we make an investment. Now in this course we're going to cover a lot of these issues. We're going to show you how information influences the movement of a stock price, how to build software to analyze and visualize these relationships, and details about how the stock exchanges work. Finally, in the last section of this course, we're going to show you how to build machine learning algorithms that you can use to build real trading strategies. Now, let's get started.
Let's do it.
The overall course is broken into 3 mini courses.
The first one is Manipulating Financial Data in Python.
In this first mini course, we show you how to read historical financial data into Python and manipulate it using powerful statistical algorithms.
The second one is Computational Investing.
In this second mini course, we show you the algorithms, methods, and models used by hedge funds and investment banks to manipulate and work with financial data.
And the last one is Learning Algorithms for Trading.
In this last mini course, we pull everything together. We take what you learned in the first 2 mini courses, show you how to take that data and use it with machine learning, algorithms like Q-learning and random forests to build trading algorithms. Now, our goal is that after you complete this course, you'll be equipped to join a trading system development team, say at a hedge fund or an investment bank. But I want to emphasize that you shouldn't immediately begin automatic trading. This course is just a starting point to teach you some of the things that you need to do that well, but again, it's just a starting point.
We will be using 3 different textbooks in this course. For the first mini course, we will be using Python for Finance by Hilpish.
In the second mini course, we'll be using a book I wrote with Philip Romero titled What Hedge Funds Really Do. It's a thin book, but it covers a lot of important material that I think you'll enjoy.
Finally, in the last mini course, we will be using Mitchell's Machine Learning.
Good news is, if you're taking the machine learning course, you'll already have that book, so you don't have to buy it again. I also wanted to mention that we're not going to cover all the material in these books, so you don't need to be worried about being overwhelmed. Hi, Dave.
Hi, Professor.
Now, you took this course recently, didn't you?
Yes.
Do you think you have to be a stock market whiz to pass this course?
No, not really. I got interested into finance only after I took your course.
The main prerequisite for this course is that you should be a strong programmer. We have a lot of assignments and projects, and we move at a quick pace. We also use Python, which may be new to some of you, so you should prepare for that challenge.
Professor, can I ask you what you are doing?
This is my Monty Python impression. You know, the Ministry of Silly Walks.
No.
Hi, I'm Tucker.
And I am Dave.
Welcome to this mini course, Manipulating Financial Data in Python. Our goal is to give you a quick introduction to the skills you'll need to work with financial data in Python. Now, some people complain about our choice of Python for financial applications.
I don't agree with those people. Python allows you to quickly prototype algorithms while also providing computational speed. It has a number of features. Firstly, it has strong scientific libraries. Second, it is strongly maintained. It is also fast if you can stick to matrix notation because lower levels are written in C.
Some other potential languages that might have made sense for this course include R and MATLAB, which are themselves also great languages for financial data. But we've chosen Python, and we'll be using this book Python for Finance in the course. Look for readings assigned in the course outline. Our objective in this class is to get you up and running quickly, to show you some real data and some code you can use to view it and manipulate it, and just give you a feeling that you know what's going on. So we're going to take you from examples of raw data all the way to visualization. Now let's get started with the data. In this class we're going to work almost entirely with data that comes from CSV files. CSV files are plain text. The C stands for comma, S stands for separated, V is values. So comma separated values. Let me show you an example of what might be in a CSV file. Most CSV files start with a header line. In this example, this is a CSV file that's telling us about weather conditions. So we've got temperature, pressure, and humidity, and that tells us what information is in the columns that are to follow. Following our header line, we have lines or rows of data. So these numbers here make up our data. Again, header row and rows of data where each data element is separated by a comma. Now the files that we're going to be working with, the stock data files, have thousands of lines and many more columns as well. Our objective for this lesson is to show you how to read in data like this, focus, say, on one column or another, and create a plot from that data. Okay, so now you've seen an example with weather. Let's start thinking about stocks. Which fields or items in a header row would you expect to see in a comma-separated value file of stock data? So here are the options: number of employees for the company, date, time, company name, price of the stock, company's hometown. Good luck. The correct answers are date, time, and price of the stock. Let me mention a couple reasons why some of these others aren't correct answers. Sure, the company name is important to know, but it doesn't change over time. So there's no need to allocate, space for this information every day over time. Company's hometown, same thing. Number of employees can be important data, and it's information that is sometimes provided via proprietary data feeds, but it's not something you typically find in a historical data file of stock prices. Okay, so let's take a look at some real stock data. We provide for you in this class hundreds of CSV files that represent the prices of stocks over time. Here's an example from one of those files that you're provided. This is data from the file hcp.csv. So here's our header row, and here's the information that you'll find in one of these files. So date, which date is the information for? Open, so this is the price that this stock opened at. In other words, in the morning when trading on the exchange began, that was the first price of the day for that stock. High, throughout the day, what was the very high price, what was the very low price, and at which price did the stock close. So when we reached 4 o'clock, what was the final price? Volume, that's how many shares of the stock traded altogether on that day. And finally, this value, adjusted close, which is a little bit different from close. And this is something we cover in the next course where we talk about finance. I'll talk about it a little bit here as well, but let me delay talking about it for a moment. Okay, I've fleshed out this data a little bit. First thing I want you to notice is that the dates start with most recent dates, and then as you go forward into the file, you find older dates. So what that means more or less is that we sort of go backwards through time in these files. Now, this is a feature, if you will, of data from Yahoo, and that's where we got our data for this class. Thanks very much, Yahoo. This is just what a real one of those files look like. Now later when we read the data in, we manage to get it in the right order, and Dave will tell you a little bit more about that. Now, I had talked a little bit earlier about adjusted close and close. Let me tell you a bit more about what that means. Now, close in this data is the actual price that was reported at the exchange when the stock closed for that day. Adjusted close is a number that the data provider generates for us, and it's adjusted, as the name implies, for certain things like stock splits and dividend payments. Now, on the current day, let's pretend for the moment that we're in 2012, adjusted close and close are always the same. However, as we go back in time, we eventually see that adjusted close and close differ. So if we go all the way back to the year 2000, we'll note that the actual price the stock closed at was $25, but this adjusted price was only $5.36. Now, what you can observe from that is, as we go forward in time, if we had purchased this stock back in 2000 and held it to 2012, what are we looking at there? About a 8 or 9 time return over those 12 years, so 800 to 900% return. If you looked only at just the actual price on the market, it's only a factor of about 2, but this adjusted close reflects things, like I said, like dividend payments and splits and so on. So that's what is in an actual stock CSV file, and this is the data that we're going to be working with throughout this course and the next 2 parts of the course. We're going to make heavy use of a library called Pandas. This library was created by Wes McKinney at a hedge fund called AQR. It's used at many hedge funds and by many people in the finance industry. One of the key components of Pandas is something called the data frame. And I'm going to show you a little bit about what that looks like. So this is the basic layout of a data frame. We have our symbols along the top. So our columns represent symbols in the stock market, like SPY, which is an ETF representing the S&P 500, AAPL, the symbol for Apple, GOOG, Google, GLD for gold. And the rows are the dates over time. So we go back as far as 2000 and come all the way up to 2015. So again, symbols from left to right, 1 column for each symbol, and time coming down like this. So here's our data frame fleshed out with a little bit of data. I made up some of these numbers, so don't. It's not intended to be gospel truth, but notice how we have, let's say this is closing prices. So we see these numbers for SPY, Apple, Google, and GLD. Now, there are some special or unusual values here. NaN, that stands for not a number, and that's Python's way of saying, hey, I don't know, I don't have information for this. The reason you see those values here is back in 2000, Google did not exist as a publicly traded company, and neither did the ETF GLD. Now these NaN values can cause problems, and we'll be talking about those in a later session. Now, as I said, this might represent closing prices, but Pandas can also handle additional data in a sort of 3-dimensional sense. So you can have a data frame that represents, again in columns our particular symbols, and in rows dates. This one can be close. We can have another one that has, for the same stocks and the same dates, volume on those dates, and adjusted close, and so on. So Pandas is a very flexible way to read in, manipulate, and plot data. Now I've shown you kind of at a high level what this data looks like and what Pandas looks like. I'm going to hand it over to Dave now, and she's going to show you some real live examples with pandas. She's going to show you how to read this data in and plot it and so on. So here's over to you, Dave.
Thank you, Professor. Hey everyone, this is Dave here. So here's an example of what the data looks like that Professor was talking about. This is basically a comma separated file, as you can see, and as you observe that the CSV is in the reverse order. But soon we will teach you how to fix that. Pandas provide a number of functions that makes it easy to read in data like the CSV file we just had a look on. Here's a code that reads in apple.csv into a data frame. So first of all, we'll have to import the pandas library. To avoid writing pandas every time we use a functionality of it, we rename it as PD. So this is the main function which we'll call the test run function. Let's have a look what's there in it. pd.readCSV, as the name suggests, will read apple.csv into a data frame, which we name it as df. As of now, imagine data frame as a structure similar to the 2D array, that is with rows and columns. Let's go ahead and print this. So here's the entire CSV file on your console. As you can see, the entire data is loaded in your console. But just to have an idea of the CSV file, you can just print the top 5 rows of the data frame. This is how you do it. Dataframe.head. .head is the functionality provided by the pandas for the data frame that would help you to view just the top 5 lines of the CSV. That will give you a rough idea of what the CSV actually contains. Let's go ahead and print this. So here it is, just the top 5 lines of your data frame. You can observe that all the columns of the CSV can be viewed here. You will also observe there is a column that is not named and has values 0, 1, 2, 3. And this is not from the CSV. These are called index for the data frame, which help you to access rows. Similarly, you can view last 5 values using df.tail. So now let's do some interesting stuff. What if I want to view rows from the data frame in between some random values and not the head and the tail? We can do something of this kind. If you want data from index 10 to 20, just add this line. Let's see the output. Here it is. All the data between the index 10 and 20 are displayed. But you must also observe that if you want data between 10 and 20, you have to mention 10:21 because 21 is not inclusive in the range. This operation is called slicing, and it is a very important operation in Python pandas which you will encounter in the future lesson. Now let's do some more processing on the data frame. We can start with finding the maximum closing value for each of the stock Apple and IBM. So here's the code. The test run function simply loops over 2 symbols Apple and IBM and will print the maximum closing value of each of the stock. Let's call the function getMaxClose along with the symbol. Here's the function that will compute the maximum closing value. Let's see what getMaxClose function does. The first step would be to read in the CSV into the data frame. The next step would be to get only the closing values from the entire data frame, which means we have to extract the column close. This is how you do it. df square brackets pass the parameter of the column name, that is close. Make sure you include the inverted commas. The last step is to calculate the maximum value, and it is as simple as calling the max function over the extracted data. Let's go ahead and print this. Here's your output. The max close for the Apple is 680.44 and the max close for the IBM is 209.5. Your task is to calculate the mean volume for each of the given symbol. You can start with extracting the volume column from the data frame and then finding the mean. I'll come back with the solution. Good luck. So here's the solution to find the mean volume for the given stock. As I explained, the first step would be to extract the volume column from the data frame. The next step is to find the mean. It can be done by calling the mean function. Let's run this code. Here you go. The mean value for Apple and mean value for IBM. I hope you enjoyed the quiz. Now let's do some plotting. It's easy to plot data in the data frame. Here's how you plot Apple's adjusted close. First, let's call a library that would help us to do this. We import a library named matplotlib. Do not worry about the details, you will learn them eventually in the further lessons. But to plot the adjacent close, we first need the adjacent close data from the data frame. And as you learned in the previous video, we can slice over the column using the square brackets. Plotting the adjacent close is as simple as calling a plot function. To show the plot on your screen, we need to add one more line, and that is plot.show. Now let's run this code. Here's your first graph. You can observe there is no x-axis label, no y-axis label, no header. Also, the data is printed in the reverse order since the CSV is in the reverse order. So the Apple prices are not moving down, they are just printed inversely. In the coming lessons, you will learn how to fix it. As of now, enjoy the power of the Python pandas that can plot information using just one line of code. Get ready to plot some data by yourself. I'll be back with a quiz. So here's the question for you. Plot the high prices for the IBM. You can approach this problem by first getting the CSV data of the IBM, followed by getting the high prices from the data frame and then plotting it. You can refer to the previous example. Good luck. Here's the solution. You can get the CSV of the IBM by using ibm.csv. The next step was to get the high prices from the data frame. df square bracket high will do that for you. And finally, you go ahead and plot it. Let's see how the graph looks like. I hope you got a graph similar to this. An advice I would like to give you at this point is, you will get hold of Python easily if you experiment. Try different options and see what works and what does not. During the course, you will realize why some things worked and why just some things failed. I'll sign off by showing you some power of pandas. We are about to plot two columns simultaneously on one graph, that is close and adjusted close, for the Apple stock. Don't worry about how to extract multiple columns from the data frame, but intuitively you use a double square brackets and pass the two column names, that is close and adjusted close. We go ahead and plot this. Here's the graph. You can observe two lines. One is blue, which corresponds to close, and one is green, which corresponds to adjusted close. Observe that we did not write code to print the legend or give color to each of the graph lines. This is the power of the Python pandas. The blue line corresponds to the close value and the green line corresponds to the adjusted close values. You will learn in the further lesson why there is a difference. That's all for now. I'll see you in the next lesson. Happy coding!
So far in this course, we've been just working with one stock at a time.
Yes, Professor.
Dave, are you a juggler?
No.
Can you juggle lots of things at once?
What?
I can juggle too.
Sorry, I can't do this.
All right, we're not jugglers. Okay, in this lesson, we're going to dive into how do we fill a data frame with the data that we want. And we're also going to touch upon a couple issues that we had that were pointed out in the previous lesson. For instance, remember when we had that issue that the dates were actually in the reverse order when we loaded them in? We're going to fix that. We're going to fix a couple other things too. Okay, just to refresh your memory, here's the kind of stuff that goes in a data frame. Our columns are the particular symbols of stocks that we're interested in, and our rows are dates. So time goes from the top of the data frame down to the bottom, and symbols from left to right. So in order to get to a data frame like this, we've got a couple problems to solve, and we're going to solve them in this lesson. So one of the first issues is we want to be able to read in particular date ranges. So if you remember from the last lesson, we just read all of it in, but what if we just want to read in a certain part of it? You know, instead of from 1995 to 2012. What if we want, say, just 2010 to 2012? Well, we got to figure out how to solve that. Something that's very special about Pandas, and one of the things that makes it very powerful, is that we can index the rows by dates. We don't have to just use a single number like 0, for instance. We need to be able to read in multiple stocks. Instead of just, say, having one, we want to have SPY, IBM, Google, and Gold all at once. We need to be able to align dates. For instance, if GLD traded on particular days and SPY traded on particular days, we want to make sure that those line up so that for each row we have the correct information for each equity on that particular date. Finally, we need to undo that problem that we discovered in the last lesson, namely that these dates in the files we read them from are in reverse order. So we want to be sure we have them in the right order when we're processing them. So these are the tasks we're going to dig into in this lesson. Here's a quiz and something important to think about. How many days were U.S. stocks traded at the New York Stock Exchange in 2014? Here are 3 possible answers. The correct answer is 252. The reason is you need to factor in weekends and holidays. And interestingly, the New York Stock Exchange has a set of holidays that occasionally differ from the U.S. government holidays. In almost all cases, almost every year, we've got 252 trading days, and this number is going to come up a lot as we continue to look at days and calculating statistics about stocks. Now here's how we're going to build that data frame. All right, we start by constructing an empty data frame that has all the dates we're potentially interested in. And Dave will show you the syntax for doing that later on in the lesson. We'll call this DF1 for data frame 1, of course. Now we want to load this data frame up with a column of data for SPY, for IBM, for Google, and Gold. And I'm going to show you step by step how we do that. Okay, so we separately read in SPY, and again, Dave will show you how to do that. Now when we read SPY, we get all the potential dates and all the prices that go with that. And in this case, we're loading adjusted close data. Note that there's many more dates here than there are here. And this is our target data frame that we loaded with the particular dates that we're interested in. One other thing to mention that I didn't mention before is these 2 days are weekend days. So you can go ahead and check your calendar and go back to 2010 and see if I'm right. Interesting thing, or just obvious thing about weekends, is the markets are not open on weekends. So if you compare this with this, look, in our SPY history, we don't have the 23rd and the 24th because SPY did not trade that day. So we've got a little bit of a mismatch there that we need to deal with. And this actually is one of the important reasons that we use SPY as a reference, because if SPY traded, it meant the market was open, and if the market was open, SPY traded. So SPY, the S&P 500 ETF, is our reference for many, many things. So Pandas has many very powerful features. One, or among those features, are the ability to do many operations that you may be familiar with from databases. In particular, one that we're going to leverage here is a join. So we're going to join this data from SPY and our empty data frame, and we're going to do a special join that says, look, we're only interested in dates that are present both in SPY and DF1. And what happens is we end up with this data according to its date in this position in our target data frame, and of course the other 2 rows as well. But note, because of the join, these 2 days are missing from SPY, and the result of the join is they are eliminated from our data frame. They're eliminated because this was the weekend. There was no trading because we know that because SPY is our reference. All right, so here's our original data frame now after we've loaded in SPY, and those weekend days that were here are gone because of that join. Now we can add more columns from other stocks. Here's one, for instance, IBM, by performing additional joins. So after this join with data frame IBM, boom, we've got this new data over here in our empty data frame. And we can repeat this process for each additional symbol that we want to add. So we'll add Google and GLD. And again, Dave will show you the syntax for doing that in Pandas in just a few moments.
Let's try to build the data frame Professor outlined. Starting with the things we need to populate the data frame with are firstly dates. We use Pandas date range method, which takes two parameters, that is start and end date. For this code, we will take a small date range, that is from 22nd Jan 2010 to 26th Jan 2010. We then call the date range function as I mentioned before, passing two parameters, start date and the end date. Let's run this code to see what variable dates has in it. The output you see is not a list of strings, but a list of date time index objects. Now what do you mean by date time index object? Let's extract the first element of this list. You can get the first element of the list by writing dates square bracket 0. Now let's go ahead and run this code. This is the first element of the list, which is a date time index object. The trailing 0 zeros for each object is the default timestamp. The index for a stock data only consists of dates, so we can ignore the timestamps for now. Next, we define an empty data frame df1 with these dates as index. We use the parameter index to supply the dates. Note that without this parameter, the data frame will have an index of integers 0, 1, 2 as seen before. Let's print this now. So here's your data frame df1. It's an empty data frame with no columns. However, as we pass the index parameter, we have index as dates, and you can see that it's a date time index object. Two major steps have now been completed. Continuing on, let's read the CSV file for SPY. In df_SPY, a temporary data frame. The next step is the heart of building the final data frame. We combine the empty data frame df1 with the temporary data frame df_SPY. We use the join function of the data frame for this purpose. Let's do it. Dataframe.join does a left join by default. So if we write a.join b, it will retain all the rows from A, but only those rows from B whose index values are present in A's index. For the remaining rows, that is the index values not present in B, Pandas introduce nans. So in this case, all the rows from the df1 will be retained, and we will get all the values for the prices from df_SPY for the given range we defined above. So in our case, all the rows from the df1 would be retained, and only those rows of df_SPY which is present in df1 will be retained. This will give us all the prices for the stock SPY in the defined date range. Let's use print df1 after the join step to make it clear. You should expect to see all the values of SPY for the given dates. Observe the output. We did not get any values from the df_SPY. What do you think? What could be the reason? Let's print df_SPY to investigate, commenting out the join lines. So let's see what df_SPY has. We told Pandas to join df1 and df_SPY, but df_SPY has an index of integers, which is not the same as the dates index that df1 uses. We fix this by informing the readCSV function that the date column in the CSV file should be used as index. We do this by using the index call parameter. make sure you give the correct column name. We also want the dates present in the data frame to be converted into date-time index objects. This can be done by setting the value for the parse dates parameter to true. Let's see if this works. Notice that the date column is now being used as the index. There is no separate integer index on the left. Now let's see what the resulting joined data frame looks like by uncommenting these lines. But before that, let's add some more parameters to the read CSV function. Note that we are interested in just two columns, which is the date and the adjusted close. We can get rid of the other columns by using the useCall parameter of the read CSV. We pass a list of column name we are interested in, which are date and adjusted close. Now let's see what's there in df1. You see now we have just the adjusted close for the SPY for a given date range. Also observe that weekend dates have nan value. Before we go ahead, let's understand that CSV has nan as string. So we need to tell the read CSV that nan should be interpreted as not a number. This is how you indicate it. One last step. We just want the dates on which SPY traded, so we can add more stocks based on these dates. Let's drop the rows where SPY is nan. For this, we use the drop_na function. df1.drop_na will drop all the rows which has nan values for the SPY. Let's go ahead and print this. Now we have built a clean data frame filled with SPY data using a selected date range and keeping only the dates that SPY traded on. Note that we use two steps for combining the data frames. That is, left joining the empty data frame with df_SPY and then dropping the rows that SPY did not trade on. This can be done in the single step using the how argument when calling join. Can you figure out what the appropriate value of how should be? Type it in the box. We are essentially trying to do an inner join. That is, we only want to retain rows common to both data frames. Note that this is not the default, hence we have to mention it explicitly. So what is the default value? What effect does it have on the result? Find out using the documentation link provided in the instructor notes. So we want to read in more stocks into a combined data frame. Start with the code we used to build a data frame with the SPY data. Then define a list with the required stock symbols. Now we can write a for loop to read and join each stock into the data frame just like SPY. So here's the for loop which takes each symbol in the symbols list and joins it to our main data frame. Let's go ahead and print this. Oops, there is an error. Reading the error message carefully, we observe that index column adjacent close has an overlap. What is happening here is that irrespective of the stock, the column we are extracting each time is named adjacent close. So the join method is confused as to what to name it in the result. Column names must be unique. As Professor described earlier, we would like each stock symbol as the corresponding column name or header. So we add these two lines. This renames the column adjusted close to the respective stock symbol. Now let's see the output. Here you go. Everything is finally in place. You must have noticed how we are carrying out essentially the same operation in different places. Why not write some utility function that we can use going forward? I have implemented one function for you, symbol to path. It accepts a symbol name as a string and returns the path to the corresponding CSV file, assuming it is stored under data by default. For example, symbol to path IBM will return data/ibm.csv. Can you finish the implementation for get data? It takes a list of symbols and dates as index and is supposed to return a data frame with stock data for each symbol within the given date range. SPY is inserted into the list if not already present in order to serve as a reference. Note that you must ensure the column for SPY does not have any nans. That is, the data frame should only contain dates when SPY actually traded in the given date range. Type in your code here. You can use test run to execute your code and submit to evaluate it against our test cases. Don't worry, there is no limit to how many times you can try. Good luck! As shown in the previous demo, there are three main steps to implement inside the for loop. The first one is to read in the data from the symbol. Make sure you specify all the parameters. Also notice how I have used symbol to path function to get the path to the CSV file. The next step is to rename the adjacent close column to the symbol name. And the last step is to join this new data with the main data frame. Now we need to take care of one important thing, that is dropping of the nans from the SPY. Subset is equal to SPY will ensure that only those rows will be dropped where SPY is nan. Also, the statement ensures that SPY is used as a reference and that we do not have any nan values in the SPY column. Let's run it. So here's the output, same as before.
Okay, let's suppose we have our nice, big, beautiful pandas data frame, and we've this time read in a lot of data. We didn't just focus on a few days. We've got data all the way from the beginning of 2010 to 2012, and we've got data for SPY, IBM, Google, and GLD. Now, suppose we want to focus on just a subset of that data. In fact, we might call that a slice. For instance, what if we wanted to look at just the values for Google and GLD between these dates, February 13, 2010 through February 15, 2010. And we want to, again, just look at Google and GLD. Well, there's very beautiful syntax in Pandas that allows you to do that. So we're going to be learning a lot more about this syntax in a later lesson, but this is sort of a preview of the very nice things you can do. To select these rows, we do a simple statement that Dave will show you later to create a date time object, and we just put the start date colon end date. And if we just write df1 bracket sd colon ed, where this is start date and that's end date, then we end up with these three rows. But we want to be more selective. We want to focus on these three rows and these columns, and we need to add one more piece of syntax that indicates these columns. So this statement will extract these rows and these columns and leave you just with this subportion or slice of df1. So if we were to execute this statement, df2 equals df1 and then this additional syntax, we will end up with this little morsel of data right here in our new data frame. Now there's lots of different ways you can slice the data. You don't have to take a group of pieces of data that are right next to each other. You can grab any different columns you want and any different rows you want. So you might build a new data frame by taking GLD and IBM, and it'll just take those two columns and split them into df2. So that's slicing. This is just a brief introduction. We're going to go into some deeper examples when we get to the lesson on NumPy.
To do any kind of analysis on the data, we need significant amount of data. So let's read data for each stock for a period of 1 year, that is year 2010. You can do this by changing the start and the end date as shown here. Let's see the data frame content now. So this is your data frame which has stock prices for the symbol SPY, Google, IBM and Gold for a year 2010. We briefly explained you slicing in the last lesson. In this lesson, we will learn how to do slicing using the data frame we just created. There are basically three ways we can slice the data frame. First, row slicing. As the name suggests, it will give us the required rows along with all the columns. This is useful when you want to compare movement of all the stocks over a subset of time. This is how you do it in the code. We use the function .ix of the data frame and just mention the start and the end date in the square brackets. Here we extract the movement of all the stocks in the month of Jan. Note that the start and the end date should be in the chronological order. If you write the 31st Jan date before 1st Jan, the data frame will give you an empty data frame. Even if you remove the .ix function and just try to print df passing the dates in the chronological order, you will get the same result. However, .ix is considered to be more Pythonic and robust, so we follow that. Now let's run the code to see the stock prices for the month of January. You can observe that we get the data only for the January month, but for all the symbols. This is known as row slicing. Second way of slicing is useful when you want to view prices of only one stock over the date range. In this case, you can use column slicing. We want to project the prices of Google for the entire year of 2010. Here is how we do it. A square bracket along with the name of the column, and do not forget the colon. To retrieve a single column, we just pass a single label. To select multiple columns, we pass a list of labels. Let's print this. And this is the output for multiple columns. The last way of slicing is to slice through both dimensions, that is rows and columns. The most robust way to do this is using the IX selector of the data frame. Let's go ahead and use it. If you need more than one column, you define them in a list like this, and date range are separated with a colon. Here you go. The stock prices for the symbol SPY and IBM over the date range 10th March to 15th March. One application of this way of slicing is to compare multiple stocks over a period of time. Pandas support many ways of slicing a data frame to suit different needs. Find out more using the link in the instructor notes.
Suppose you've got a data frame. It's pretty easy from the data frame to make a plot. In fact, the syntax is as simple as this. Pandas will take this data and create a nice chart that looks about like this. It'll give an individual color to each time series and give you a nice legend telling you which is which. Now, one problem with viewing data like this is, for instance, at this time, by the way, these numbers are made up, but it's often the case that stocks are priced at significantly different levels. So in this example, say Google had a very high price and the other stocks had low prices, and it's hard to look at them sort of in a good way comparatively when they have these widely varying prices. So what we'd like to do instead is be able, say, to have them all start at one single point here, say that's 1.0, and then go out from there so we can compare them on an apples-to-apples comparison. So we'd like to end up with a chart that looks like this, where everything starts at 1.0, and we can compare them on an equal basis going forward. Okay, let's try a quick quiz. What is the best way to normalize price data so that all prices start at 1.0? So here are two choices, a nested for loop or a one-line expression. Good luck. Well, it was a little bit of a trick question because both of these will accomplish the same goal, namely normalizing everything so that normalizing everything according to the first row. This method uses two nested for loops to go through each date for each symbol and then make the division. This is the preferred method, however, and that's because it's elegant, just a single line. We divide the entire data frame by its first row. The other reason that this is the way to do it is because it's much, much faster. This ends up being executed in C at lower levels, whereas this will be executed at the higher level, the higher interpreter levels of Pandas and Python.
Carly Fiorina rightly states that the goal is to turn data into information and information into insight. So let's better understand the data by improving our plots. We will need the matplotlib library for this purpose. Specifically, we import the matplotlib pyplot and rename it as PLT for ease of use. First, let's define a trivial plot function. we define a plot data function which will essentially plot the contents of the data frame. We pass a data frame to it and use its plot function to plot all the data in it. Let's see the output. Remember, to see the graph, we have to call the show function from the matplotlib library. Observe that x-axis has dates and y-axis has prices for all the 4 stocks. The graph still looks incomplete. We need to add details like give a name or title to the graph, add x and y-axis labels. We will give name to the graph by passing in parameter title. This should be customizable. And here we pass the value of the title to the parameter title of the data frame. For x and y-axis labels, we need a handler to the plot which the data frame generates. The output of df.plot is such a handler. You can imagine it as an object. We name it ax for axis. Now we call setXLabel and setYLabel on this object to give the x and y axis some meaningful labels. The desired label are passed as a parameter to the function set_xLabel and set_yLabel. Remember that setXLabel and setYLabel are the function of the object that we got from df.plot. You can also use the font size parameter in df.plot to make the graph more readable. Now let's see the modified plot. So here's your detailed plot with x label, y label and a title. You now know how to read stock data, slice it and plot it. The challenge for you now is to write a code to plot the values of SPY and IBM over the date range. Go ahead and write your code in this function. The clue to this is use slicing. To complete this, first slice using the notation you learned earlier. Once you get the desired data set, the next step is to plot by calling the plot_data function we defined earlier. Recollect that plot_data takes the parameter, data frame and title. Let's see what we get now. Here's the plot showing the changes in the stock prices for SPY and IBM for the period of March. Let's analyze the graph that we had plotted for the 4 stocks. You see the 4 stocks are over multiple ranges. But we need to observe the movement of the stock. By movement, I mean how much the stock went up or down as compared to the others. To do this, we need to normalize the prices of all the stock. We do this by dividing the values of each column by day 1. This will ensure that all the stocks will start with $1. Power of pandas and Python is that we can do this in one line. Let's add it. We define a function normalize data and pass the data frame to it. First, we want all the values of the data frame. Hence, we just type the name of the data frame, which is df. Now we want to divide all the values of this data frame by the first row of it. So we extract the first row using row slicing. This will give us the first row. Now we will just divide it. Let's see how the graph changes. Observe all the stocks start with price 1. And now you can see the changes, that is the stock movement. That's it for now. I will be back soon with more coding. Till then, enjoy the power of the Python and happy coding.
In this lesson, we're going to learn about the NumPy numerical library. NumPy is a Python library that acts as a wrapper around underlying C and Fortran code. Because of that, it's very, very fast. NumPy focuses on matrices, which are called ND arrays. The syntax is very similar to MATLAB, so if you've used MATLAB before, it'll look familiar to you. NumPy is one of the important reasons people use Python for financial research.
Now, how does NumPy relate to pandas? Well, I said just a moment ago that NumPy is a wrapper for numerical libraries. Well, it turns out that pandas is a kind of wrapper for NumPy. So remember our traditional data frame here with our columns being symbols and our rows being dates. This data frame is just a wrapper around this ND array. Access the columns with symbols and the rows by dates. But you can, in fact, just treat this inside part as an ND array directly. If you use this syntax in Python, that pulls these values out and lets you access it directly in an ND array. You don't really need to do that though. You can, if you like, treat a data frame just like a NumPy ND array. And so we're going to assume in the rest of this lesson that we're just working with an ND array. And like I said, you can use all of these mechanisms that we're going to show you with ND arrays and with data frames directly. What you get if you create something as a data frame, as we'll see in a lesson a little bit later, you get many, many, many more routines. And you can treat it, like I said, just like an ND array, but you get a vast new number of statistical functions and so on. Consider an ND array, ND1. I'm going to show you now how to access cells within that. Now the notation at first might seem sort of familiar, but there's some new and different things that you probably haven't seen before. So the usual syntax is the name of your ND array, bracket, the row and the column. So again, these are our rows. So row indicates which row we're using, column which column. It's important to know that in NumPy, our columns and rows begin at 0. So this element is ND1 bracket 0, 0. It then continues, of course, 1, 2, 3, 4 in the rows, and in the columns 0, 1, 2, 3. Before I tell you, see if you can guess how to address this cell. The answer is that this cell is ND1 3, 2. 0, 1, 2, 3, 0, 1, 2. Now this is probably the kind of stuff you've seen before. It turns out though that NumPy is much more powerful and can do interesting and different kinds of slicing. What if, for instance, you wanted to address this subportion of the ND array? How could you indicate that? NumPy uses a special symbol, the colon, to let you indicate ranges. So we can indicate this range in rows with 0, 3, which indicates the 0th to the just before the third row. And in the columns, we've got 0, 1, 3. So this syntax indicates starting at the 0th row to just before the third, and the first column to just before the third, and in fact captures this region. The key thing to remember here that's a little bit tricky is that this last value is one past the one that you actually want to include. So for instance, this is column 3, but it's not included. Now if we just use the colon by itself, that indicates, for instance, if we place it in the rows position, that we want all of the rows. So you don't have to use the colon just to indicate a range, you can use it by itself for all of them. Now look at this statement, see if you can figure out which part of this ND array it refers to before I show you. It is this region right here. So it's all the rows and column 3, 0, 1, 2, 3. So it's this section right here. NumPy includes some special syntax that lets you refer to the last row or column. So for instance, the last row here you can indicate with -1. Second to last row would be -2. So if we wanted to refer to these two cells here, we would take advantage of this -1 syntax. So -1 indicates that last row, and then to get these two columns we would use 1, 3, 0, 1, 2, and then we don't include the last one there. There is a bunch of new syntax. I hope that you find it exciting. This is really one of the most powerful aspects of Python and NumPy, and it really enables you to do some interesting things. Now we've got a quiz to see if you can figure out how to use this new syntax yourself. Now that we've shown you how to address slices of ND arrays, we're going to give you a little quiz to see if you can figure something out. Suppose we have these two ND arrays, ND1 and ND2, and we want to replace some of the values in ND1 with these values from ND2. Here are 4 alternatives. See which one you think makes the most sense. Of these 4, this one is the right answer. Here's why. This is the only left-hand side that singles out these correct rows starting at 0 and ending at 1, and these correct columns, again starting at 0 and ending at 1. If you look at the right-hand side, here is a little bit of new syntax that you hadn't seen before. We indicate the rows second from last by -2, so that's what that -2 means, and a colon with nothing after it means go all the way to the end. So we've singled out these rows, and this indicates these two columns, so that's why this one is the correct answer. Now I'm going to hand it over to Dave, and she's going to show you how to do all these things directly in Python syntax. Here's to you, Dave.
You can access the underlining NumPy array within a pandas data frame using the values property. But you can also create NumPy arrays from scratch. There are many ways to create an array. Let's start with creating a one-dimensional array from known values. NumPy has an array function which can convert most array-like objects into an ND array. What do you mean by ND array is n-dimensional array. Let's see how this works for Python list. To start with, we need to import the library NumPy and we rename it as np for the ease of use. Next, we simply call a function np.array and pass a list which has value 2, 3, 4. Note that this function can take as input a list, a tuple, or other sequence. Check out the documentation for the array function and ND array type for more information. Now let's see the output. The output you see here is not a list, but it is an array. Let's go ahead and create a 2D array. Now, if you want to create a 2D array, we simply pass in a sequence of sequences to this function. Each tuple enclosed in round parentheses serves as one row in the resulting array. We could also have passed a list of list. This is called sequence of sequences. Let's go ahead and print it. Here is the output. And as expected, there are 2 rows and 3 columns. This function is mainly useful when you have a list of sequence of values and you want to convert them into NumPy array. NumPy also offers several functions to create empty arrays with initial values. For certain computations, these help avoid growing arrays incrementally, which can be an expensive operation. Let's start with creating an empty array. The empty function takes the shape of the array as input. The shape can be defined as a single integer, as we did over here, for creating a one-dimensional array or a sequence of integers denoting the size in each dimension. For a two-dimensional array, a sequence of 2 integers is needed, that is the number of rows and the number of columns. For this example, we will create an empty array with 5 rows and 4 columns, passing in a tuple with values 5 and 4. So here I pass a tuple with values 5 and 4. In case you need a 3-dimensional array or any greater number of dimensions, you can just add another number to the sequence. This will give you a 3-dimensional array with depth of 3 and each depth having 5 rows and 4 columns. For this lesson, we will only work with 2-dimensional arrays. Now let's check the output. Strange. The empty array is not actually empty. What happens is that when we call numpy.empty to create an array, the elements of the array retain whatever values were present in the corresponding memory location. These are effectively random values that depend on the state of the computer's memory. Also observe that by default the elements are the floating points. Next we create an array full of ones. Like the empty function, we pass in the number of rows and columns as a sequence. To create an array full of ones, you call the one function and pass the sequence which has number of rows and number of columns. You can expect this time to have an array of 5 rows and 4 columns with all the values equal to 1. Let's go ahead and check this. Here it is, an array with 5 rows, 4 columns and all the values of the array equal to 1. We notice that the default data type of all the values in the array is float. Fortunately, you can change this when creating the array. What parameter do you need to add to this function to create an array of integers instead? Type the name of the parameter and the correct value in the corresponding boxes. Documentation for the array.ones function might be helpful. dtype is the parameter we pass to the function to specify the type of the value we want in each array location. Here we define the values to be integers using numpy data type np.int. Just as a matter of fact, NumPy supports a much greater variety of numerical types than Python. Let's run this. Here it is. The array now has integer values, and since we defined the array as ones, it has all the values as 1. Just like function empty and ones, you can create an array full of zeros using the zeros function. All these functions accept the dtype parameter. Before moving forward, I would like to mention that we can also create n-dimensional array using the low-level NumPy function ndarray. But ones, zeros and empty provide a more friendly interface for creating arrays and are hence generally preferred. Refer to the documentation links in instructor notes for more information. NumPy also comes with a bunch of handy functions to generate arrays filled with random values. These functions are defined in NumPy's random module. The random function generates uniformly sampled floating point values between 0 and 1, with 0 inclusive and 1 exclusive. More formally, we can say that it generates values in the half-open interval 0.0 and 1.0. Let's go ahead and print this. Here is the generated array with 5 rows and 4 columns. Note that we passed the array shape as a tuple. A slightly variant of this function is rand, which directly accepts a sequence of numbers as arguments instead of a tuple. It is otherwise equivalent. Observe that we directly passed the values of the rows and columns to the function and did not define a tuple. Here it is, the array with same shape as before, 5 rows and 4 columns. NumPy provides this to achieve a greater compatibility with the more established MATLAB syntax. We however recommend using a more consistent NumPy function that explicitly accepts a shape tuple. Now both the function rand and random sample uniformly from the range 0 and 1. What if you wanted to sample from a different distribution? To sample from a Gaussian or normal distribution, we can use the normal function. We call the normal function from numpy.random and pass the shape of the array we require. Let's run this. The code produced a 2×3 array of random numbers with a standard normal distribution, that is 0 mean and unit standard deviation. You can change the mean and the standard deviation as well. Let's see how to do that. We change the mean to 50 and standard deviation to 10. Now let's see the output. Notice that the values are centered around 50. To generate integers, we can use the randint function in one of the several ways. Passing two values 0 and 10 will notify randint to generate a single integer between the range 0 and 10. We can also specify randint how many integers do we want between 0 and 10 by specifying the size attribute and giving it a value. So this statement will give us a 1D array of 5 integers between the range 0 and 10. Going forward with that, we can pass a tuple value to the attribute size, which will create a 2D array with all the values between the range 0 and 10. Now let's see the output. These are the single random integers between the range 0 and 10. Next, we created a 1D array with 5 values. Note that we mentioned the number of values needed in the one-dimensional array with the parameter size. Passing a tuple to the size parameter gave us a 2D values, and also note that all the values of the array are between 0 and 10. Check out the other random sampling routines on the NumPy website for more distribution and usage variations. Find the link in the instructor's notes. Any NumPy array has a number of attributes that describes it, in addition to the elements it contains. One of the most useful one is shape, essentially a tuple containing the number of rows and columns or height and width of the array. We have already seen how to specify this when creating arrays. The shape of the array A would be 5 rows and 4 columns. So this is your array. Now let's see how to access the shape of the given array by using the shape attribute. A.shape will give you the shape of the array. Let's run it. Array.shape will return you a tuple with the first value specifying the number of rows and the second value specifying the number of columns. Next we will learn how to individually access number of rows or number of columns. A.shape 0 would return the number of rows and A.shape 1 would return the number of columns. Let's check the output. Here you see that the number of rows are correctly extracted as 5 and number of columns as 4. If you have more dimensions, you will have additional elements in the shape tuple. The number of dimensions in an array can be found by simply asking for the length of this tuple. A.shape will return a tuple and the length of that tuple would inform us what is the dimension of the array. It rightly tells us that the dimension of the defined array A is 2. Okay, how about total number of elements in an array? Yes, for a 2D array, it will be the product of number of rows and columns. But if you had more dimension, this calculation could be a little complicated. Fortunately, we can retrieve the number of elements directly using size attributes. A.size will give us the number of elements present in the array A. We can expect the output to be the product of the rows and the columns, which is 5 into 4, which is 20. Let's check it. As we expected, the output is 20, which means there are 20 values in the array. Attributes like size and shape are very useful when you have to iterate over array elements to perform some computation. You can also access the data type of each element using the dtype attribute of the array. Let's check the data type of the values present in array A. In this case, our array elements are of the type float64, that is 64-bit floating point numbers. Next you will see how to perform various mathematical operations on ND arrays. Let's use a random array of integers. Let's create an array with shape 5 rows and 4 columns. Let's see the output. So here's an array with 5 rows, 4 columns and all the values between the range 0 and 10. Note how we used seed, the random number generator, with a constant to get the same sequence of numbers every time. Let's run again and see if the output remains the same. You can see that we have the same values for the array. Summing all the elements in an array is as simple as calling the function sum on the array. Here is our array A and we call the sum function on it. Let's check the output. This is our array and this is sum of all the elements present in the array, which comes out to be 79. We can also sum in a specific direction of the array. What I mean by direction is along rows or columns. NumPy gives this direction a special name. It is called axis. Axis is equal to 0 signifies rows and axis is equal to 1 indicates columns. Remember this terminology as you will use it frequently. Let's code to make things clear. Passing the parameter axis along with the specific value will give you the sum along that axis. To understand this, let's first see the output. To get the sum of each column, we pass the value to the axis attribute as 0, and to get the sum of the rows, we pass the value as 1. To understand this, imagine if you wanted to sum the values of each column, what would you iterate on? You would say something like, for each column, sum all the values of each row of that column. So you would essentially iterate over the rows. Hence we pass axis equal to 0 to compute column sums and similarly axis equal to 1 for row sums. Observe the output when we passed axis equal to 0. We get 4 values. These are basically the sum of each columns. And when we passed axis equal to 1, we get 5 values which are sum of each rows. Let's go ahead and try some basic operation like finding minimum, maximum and mean of an array. So if I want minimum along columns, I have to go through each row of each column, so axis equal to 0 to get the minimum of each column. To get the maximum of each row, similarly we call a max function and pass axis equal to 1. Just calling a.mean, that is array.mean, will give us the mean of the entire array. Of course we can get mean along each axis as we did for max and min. Observe the output. Minimum of the first column is 1, which is showed over here. This value is essentially minimum of the first column. This is of second, this is of third, and this is of fourth. Similarly, for maximum of the each row, you can observe that for the first row the maximum is 5 and it is shown here. The mean of all the elements is 3.95, which is calculated using the mean function. There are many more functions which you can experiment with. Check the documentation link in the instructor's notes. So far we have seen how to compute certain measures. How about finding the position of some element in an array? Can you implement this simple function to find the index of the maximum value in the one-dimensional array? Remember, NumPy is your friend. To get the maximum value in a given 1D array, you could loop through the array, finding the maximum and keeping track of an index. But NumPy can help you do this in a single call. You must have seen argmax and argmean used to describe optimization equations. This is the same idea. Let's check the output. So the argmax function returned us the maximum value along with the index. Now for multidimensional arrays, finding and representing indices is a little tricky. But NumPy provides some utility functions like unravel_index to help you out. We claimed that NumPy is fast, very fast. So let's confirm this. But before that, we need to learn how to time a particular operation. We need to import a library for that. We import the time library to help us know how fast our operation is. We use the time function from the imported library. The idea is to capture the time snapshot before the operation and then again capture the time snapshot after the operation is performed. We then subtract the two times. Simple, right? Let's check the code. Here we will check how much time a Python print statement takes. So we capture the time before the print statement and then record the time after the print operation is performed. Then finally subtract t2 minus t1. Let's run the code now. Here we get the time taken by a print statement. Oh, the number is really very small. Now when we know how to time an operation in Python, let's check how fast NumPy is. Let's define a really large array so that the time taken for the operation will be significant to compare. So here is our large array of 1000 rows and 10,000 columns. Before I go ahead, I would like to mention that this is just a demo code to show the speed of NumPy. So I will be giving a high-level explanation of this code. Moving ahead, we will be comparing how to compute mean of the array using NumPy and using standard iteration. Here is the manual mean function which computes the mean of the values in the defined array. We iterate over each row and for each row iterate over each column. We then sum present all the values throughout the array. Finally, we divide by the size of the array and hence we get the mean. In case of using NumPy for calculating the mean, we just write array.mean to get the mean of the entire array. HowLong function will just compute the time each method takes. Now let's check what's the time difference. Do you see the difference? This is the time taken by the numpy.mean function to calculate the mean of the entire array. And remember, the size of the array are in thousands. On the other hand, the time taken by the manual method of iteration is about 5 seconds. Hence proved, NumPy is super fast. We also compute the rate of how fast the NumPy is. And the numbers are crazy. It's about 290 times faster than the manual for the loops. Observe that NumPy not only makes the code more cleaner as compared to the manual method, but is about 290 times faster than other method. Don't you think it's just awesome? Accessing array elements is straightforward. You can access a particular element by referring to its row and column number inside the square brackets. The first integer over here denotes to the row number and the second integer denotes to the column number. Let's see which element do we get at position 3, 2. Observe that the element which we get actually belongs to the fourth row and the third column. But note that the row and the column indexing start from 0. Hence, if you want an element of the fourth row and third column, you pass the parameter as we did, that is 3, 2. Now let's do some interesting stuff. Accessing elements in ranges. If I would want to access elements from first through third column in the 0th row, here is how I would do it. This operation is called slicing, as explained before using data frame. Let's read out the slicing operation. For the 0th row, get values from first through third column excluding the third column. Now let's run this. So here's the output. For the 0th row, first through the third column excluding the third column. This was just column slicing. We can combine row and column slicing and get a subset of the array. If I would like to access the top left corner of the array, I would do this as follows. We can combine row and column slicing and get the subset of the array. Here is the top left corner, which has elements at position 0, 0, 0, 1, 1, 0 and 1, 1. One last interesting thing in slicing which I would like to bring in front of you. You see a lot of numbers over here, so let's break it down and read it. The three numbers separated by the colon, this is not accessing the third axis, but a slicing of the form n is to m is to t. Will give you values in the range n before m, but in steps of size t. Hence this statement will give you values of the column 0, skip the values of the column 1 and then give the values of the column 2. Let's run this. As explained, you get the 0th and the second column with all the rows. Seems like magic, right? Moving forward, it is good that we can access elements in array. But another important operation is assigning values to specific location in array. This will give us access to the element at the position 0, 0 in the array. And using the assignment operator, we can assign a value 1 to it. Let's see the output. Here you go. This is the original array where we replaced the element at position 0, 0 with 1. But that's not all. With a minor change, you can assign a value to the entire row or column. Let's do it. This will give us access to the 0th row and we assign the entire row a value of 2. Let's run this. Using similar operation and column slicing, we can also assign an entire column a single value. Now what if we need each column or row to have different value and not the same as we did over here? Let's see how we can achieve this. Yes, this is a list of values. You can assign a list of values to a row or a column. Here we assign this list of values to column number 3. But make sure you keep an eye on the dimension. That is, for this example, if you have 5 rows in an array, the list should have 5 elements. As you can see, all the list values have been assigned to the third column. So now it's your turn. Go ahead and try more row and column slicing. There are various options of indexing, and that gives NumPy indexing great power. NumPy array can be indexed with other arrays. It is just one another tool which can be used to make process of accessing values in array easy. To start with, we create a one-dimensional array of 5 random values. Next, we create a variable indices which is also a one-dimensional array. But the elements of this array, which is 1, 1, 2, 3, are actually the index we need to access. That is, we want the value at index 1, again at 1, 2, followed by 3. Next step, we'll learn how to use this indices along with the array to access the desired values. Yes, you saw that right. Just passing the array of indices to another array will give us the values. Let's check the output. So here is the output. Observe that the length of the indices array and the returned array is the same. Also, it returned value from array A at index 1, 1, 2, 3. It is a bit difficult to understand the application of this now, but this is a tool you would like to use once you get hold of it. We can do such indexing using multidimensional array as well, but things get complicated with creating multidimensional index array. These are just few interesting ways of indexing. There are a lot more out there for you to experiment with. Check the link in the instructor notes. Next, we will be working with Boolean arrays. In simple terms, arrays with values true and false. This can also be used for indexing. Indexing using Boolean arrays is very different as compared to index arrays we learned previously. Imagine a situation where we want to get all the values from an array which is less than mean of the entire array. The first step to solve this problem would be to calculate the mean. Consider a two-dimensional array. As we learned before, we will calculate the mean using the mean attribute of the array A. Let's check what the mean is. According to our problem, we want all the values from the array which is less than mean. Mean is 14.2. You can imagine that the solution would contain values 10, 10 again, 5, 0, 0 again, 2, and so on and so forth. If you need all these values, one way is to run the for loop over the array and get them. But using NumPy masking, we do this in one single line. To read this operation, it would be for each value in array A, compare it with the mean. If it is less, we retain the value. Let's check the output. Here is the values which we expected in the form of list. Now to go ahead with this concept, we can also replace these values with the mean value. We just assign the mean value to masking operation we performed before. Let's see the output. Observe that all the values previously less than mean have been replaced by the mean. This is one of the important operations that shows the power of the NumPy and justifies its extensive use throughout. Arithmetic operations on arrays are always applied element-wise. Let's start with simple multiplication operation. Here we define a simple array so that we can easily track the changes. This will multiply each element by 2. Let's check the output. When using arithmetic operation, a new array is created and the values are stored in that array. So our original array A still holds the same values. And this is our new array which we get after multiplying array A by 2. Observe that it is element-wise multiplication. Let's try division. Here we use the division operation to divide each element of array A by 2. Let's check the output. Observe that when you divide 1 by 2, you get a value 0 over here instead of 0.5. This is because both the array and the divisor are integers. If we would do 2.0 instead of 2, you will get float values. Keep this point in mind before performing division in general. That is, int divided by int will give you an integer output. To get float values, you need at least the numerator or the denominator to be a float value. Let's check the output. Observe that we could successfully get a floating point value instead of 0. How about arithmetic operation using two arrays? We will start with addition. We create another array B with these values. Now let's just add A and B using the plus operator. As mentioned, this is element-wise. This is our new array A plus B. One important thing to note here is that the shape of A and B should be similar before the operation A plus B, else it will throw error. Similar to the addition, you can perform subtraction. Now let's move ahead with multiplying two arrays. This is interesting because unlike other many matrix languages, multiplication operator when used with two array will not give you matrix product but will do element-wise multiplication. That is, element at position 0, 0 in array A is multiplied only with the element at position 0, 0 in B. Let's print the multiplication of matrix A and B. Can you observe element-wise multiplication? But the next question would be, what about matrix multiplication? How do you achieve that? Like for everything NumPy has a function, it has function called dot which performs matrix multiplication. Similar to multiplication, division of two arrays can be performed. Just include division operators between the two arrays. Let's check the output. As seen before, since array A and B are integers, we get the final array in the form of integers as well. If you want to see floating values, convert one of the arrays to float. Well, that's all for now. Keep practicing. All the operations and functions explained in this lesson are those which will help you perform computation. But there is a lot more to learn. Check out the link in the instructor notes. I will meet you in the next lesson with some more coding. Happy coding with Python and NumPy till then.
Are you ready, Dave?
Ready for what, Professor?
We're going to start some serious number crunching now.
What do you mean?
Well, in this lesson, we're going to unleash the power of Python. We're going to show folks some tools that enable them to calculate all kinds of important statistics on time series data.
Well, what are we waiting for?
Let's go.
In this lesson, we're going to take a look at the various kinds of statistics that we can take on time series data. Let's start first with global statistics. Consider our trusty data frame, DF1, with columns for SPY, Exxon, Google, and Gold. We can take the mean of each of these columns very simply with a statement like this. This statement will take the mean of each column and put it in the appropriate location of a new one-dimensional or row-wise ND array. Now, because this is a data frame, and remember, a data frame augments NumPy and provides a lot more functionality, it's sort of a ND array on steroids. We get lots and lots of functions we can access in this way. We already mentioned mean. In addition to mean, we've got median, standard deviation, sum, prod, mode. Altogether, there's at least 33 global statistics you can compute in this way, and they're always adding more. Let me hand it over to Dave, and she's going to show you how to do this in code.
Let's do some coding to get an idea of what Professor just explained. Starting with defining a symbols list, having symbols like SPY, Exxon, Google, and Gold. We then move ahead to build our data frame DF just like we did in couple of lessons before. So DF is our final data frame. Now let's start computing statistics. First we compute mean. We need mean of stock prices for each symbol, and dataframe.mean will do this for us. As Professor explained, it computes mean for each column, and our columns denote one stock each. So we get mean for all stocks in just one line of code. So to compute the mean, we just called the name of the data frame df.mean. Let's check the output. Note how pandas prints the mean for each symbol properly labeled. Also, here is the graph with all the symbols and their data. Similarly, we can compute median and standard deviation. Let's do it. We compute the median of the data frame by calling the median function. Remember the difference between the mean and the median. Mean is the average of a set of values, that is, their total sum divided by number of values, whereas median refers to the value in the middle when they are all sorted. Now let's try standard deviation. We compute the standard deviation by calling the function std over the data frame. Let's check the output. Mathematically, standard deviation is the square root of variance, but more intuitively, it is a measure of deviation from central value. Here the central value is the mean. A higher standard of deviation, like here for Google, indicates that the stock prices has varied a lot over time.
We're going to introduce a new kind of statistic now called rolling statistics. And as opposed to, say, just taking the mean across a whole period of time, we take sort of a snapshot over windows. And I'm going to show you what that means in just a moment. Now on that last slide, we computed a global mean, which would be something about like this on this data. A rolling mean is a little bit different, and here's how it works. Let's suppose we're going to take a 20-day rolling mean. We go, starting from here, 20 days, so right about here, and then we take the mean of all that data behind us. We can draw a little box around that. This is called the window, and in our case it's 20 days. So we average all these values and we get one mean, which is this point. We then move the window forward one day and we take another mean. Here's our next mean, which is a little bit higher. Now if we do that every day over this entire year, so this is S&P 500 over the year 2012, we get something that looks about like this. You can see essentially that it's a line that follows the day-to-day values of whatever it is we're tracking, but it lags a little bit. It's sort of a smoothed and lagged line, and this is called the rolling mean. We can compute statistics like this, just like the rolling mean. We could do standard deviation, we could do mode, median, and so on. All of those statistics I showed you just a moment ago can also be used as rolling statistics. In a lesson in the next mini course, we're going to spend a lot of time talking about technical indicators. And this is actually one of them, this rolling mean. It's called, by technical analysts, a simple moving average. And one thing they look at is places where the price crosses through the rolling average. So in this case, the price is moving down through the 20-day mean. Now, a hypothesis that I'm not saying I support, but a hypothesis that many who conduct technical analysis is that this rolling mean may be a good representation of sort of the true underlying price of a stock, and that significant deviations from that, like this one here, eventually result in a return to the mean. So if you can look for, say, significant deviations like this one, you might find, say, a buying opportunity here. A challenge, though, is to know, hey, when is that deviation significant enough that you should pay attention to it? Assume we're using a rolling mean, and we're tracking the price here in blue, and we're looking for an opportunity to find when the price has diverged significantly far from the rolling mean, that it might be an opportunity for, say, a buy signal or a sell signal. How can we decide that we're far enough away from the mean that we should consider something like that? So the question is, which statistic might we use to discover this? Here are a few options. Give it some thought and check the box you think makes the most sense. The answer is rolling standard deviation, and we'll show you why in the next node. Returning to that question of how can we know if a deviation from the rolling mean is significant enough to warrant a trading signal, we need some way of measuring that. And John Bollinger in the 1980s came up with something he calls Bollinger Bands. And whenever you mention that, you have to put a little R there, because he has registered Bollinger Bands as a trademark. And if you don't do that, they'll come after you. Anyhow, how might we measure that? What Bollinger observed was that we ought to take a look at the recent volatility of the stock. And if it's very volatile, we might discard movements above and below the mean. Whereas if it's not very volatile, a similarly sized movement maybe we should pay attention to. His idea then was to add a band 2 standard deviations above and 2 standard deviations below. Now, I'm not going to make any comment as to how effective this method is. That's something for us to assess in the next mini-course. But the theory, anyways, is that when you see excursions up to 2 sigma or 2 standard deviations away from the mean, you should pay attention. And in particular, if we drop below that and then up back through it, that is potentially right there a buy signal, because the hypothesis there is that we've gone quite far from the simple moving average and we're now moving back towards it. So if you buy there, you should anticipate positive returns as it climbs back through the average. Similarly, here, where you see it punch through the top and then go back down through, that's potentially a sell signal. And as you can see in this particular case, if we had bought here and sold there, we would have done great. But if you look at many examples of this, it's not always so great. So don't run off and start trading, but just be aware that this is an example of a technical indicator and how you might involve it in a trading strategy. Dave is now going to show you how to read in data like this, compute a rolling mean, and chart it. And once again, I want to repeat that I'm not necessarily endorsing technical analysis here, although I think it can be very powerful, just introducing some of these concepts to you. And again, in our later mini course, we're going to talk a lot about these approaches. Okay, here's to you, Dave.
For working with time series data, pandas provide a number of functions to compute moving statistics. We use rolling mean function to compute the rolling mean of the SPY. Note that rolling mean is not a data frame method, but it is a function with the pandas library. So we wouldn't be able to call df.rollingMean. Instead, we pass in a set of values for which rolling mean has to be calculated as the first parameter. Now let's code for this. Firstly, let's get SPY data in our data frame for the year 2012. We also go ahead and plot the SPY data. Notice that we retain the matplotlib access object so that we can add to it later on. Next, we call the rolling mean function from pandas library and pass in two parameters. As explained before, the first parameter would be the values for which the rolling mean has to be calculated. Hence, we pass our data frame containing SPY values. The next parameter is the window size for which the mean will be calculated. We use a period of 20 days. This will return a series consisting of the rolling mean. It is always good to visualize the rolling mean, so we plot this series using the plot function. This time, while plotting the rolling mean, we pass in the matplotlib access object so that it gets added to the existing plot. Notice that we specified a label is equal to rolling mean. This will be used to create a plot legend. Let's add the legend and some axis labels to our plot. So here we add our legend to the upper left corner of the plot, add the X label and the Y label. Finally, we are all set to view the plot. Observe that the rolling mean has missing initial values. The reason is that we defined a window period of 20 days. So the first 20 days there are no values. Also notice how it follows the movement of the raw prices and is also less spiky. It's quiz time. Professor explained to you how to get Bollinger Bands and now you get to try it yourself. Here's the data frame containing the stock prices for SPY for year 2012. Now computing Bollinger Bands consists of three main steps. First, compute rolling mean, followed by computing rolling standard deviation, and then finally computing the values for the upper and the lower bands. We want you to implement one function for each step. You can call each function in this manner. Note that in this case we use a window size of 20 for calculating rolling statistics, but we should be able to vary this. Finally, we plot the original prices, rolling mean, and the Bollinger Bands. Let me start you out with one of the functions. Here is how I would implement getRollingMean. Now go ahead and write code to compute the rolling standard deviation and calculate the upper and the lower Bollinger Bands. Wondering how to compute rolling standard deviation? Check out the Trusty Pandas documentation for that. Now refer back to the previous video if you forgot how to calculate Bollinger Bands. Note how we calculated the rolling mean. The rolling standard deviation can be computed in a very similar way. Pandas provide a function called rolling_std to do this job. We simply pass in the values and the window size. Now on to Bollinger Bands. Recall that upper band is 2 standard deviation above the rolling mean. Let's type this in our code. Here we add 2 times the value of the rolling standard deviation to the rolling mean. Though the mean and the standard deviation values are in the form of series, the mathematics still works. It is similar to the arithmetic operation on NumPy arrays, which is done element-wise. Next, let's calculate lower band in the similar way. Here I subtracted 2 times the rolling standard deviation values from the rolling mean. Note that we return the values for the 2 bands together. These are received back when the function is called. Let's see if a function computes Bollinger Bands correctly. Looks good to me. Observe the selling and the buying points. You can play with the window size and see how the bands change. You could also try computing bands at different deviation away from the rolling mean.
Now we're going to look at something called daily returns. Daily returns are one of the most important statistics used in financial analysis. So let's consider first here this time series S&P 500 in 2012. What daily returns are is simply how much did the price go up or down on a particular day. So for instance, on this day it went down a little, on the next day it went up a lot. Daily returns are calculated easily using a simple equation here. So the daily return for day T, let's say today, is simply today's stock price divided by yesterday's stock price minus 1. Let me show you an example. Let's suppose on this particular day the price went from $100 yesterday to $110 today. The daily return then for that day is 110 divided by 100 minus 1, or 1.1 minus 1 equals 0.1, which is 10%. So that's how we calculate daily returns. Now one thing to remember is this is a kind of statement you might put in a for loop where you iterate over individual days. Don't do that. Use the NumPy syntax we showed you where you can do this in a single statement with no for loops. Here's what a chart for daily returns might look like. Everything is scaled now from minus 10% to plus 10%, and what we see here is a daily return for each day. If it was a positive return, of course it's positive, and negative if it were negative. Remember that day when we calculated we had a positive return of 10%. That corresponds to that point right here. And for instance, here on the next day we had negative daily return. That corresponds to that point right here. Key thing to remember here is this is a line that sort of zigs and zags, usually close to 0. And if you were to take the mean of all these values, because we've had a generally upward moving trend here, our mean would probably be a little bit positive above 0. Where looking at daily returns can be really important and revealing is to compare daily returns between different stocks or different assets. So for example, we might compare how Exxon moves in comparison to S&P 500. As one example, if you take a look at this section here, you can see that when S&P 500 went up, Exxon went down. And that's revealed here in this section of the daily returns. We're going to spend a lot of time in some future lessons looking at how these statistics, specifically how daily returns between different assets can be revealing. Dave is going to show you now in Python how to calculate these daily return values. Here's to you, Dave.
Ta-da! It's quiz time again. Can you write a function to compute daily return values? It should take a data frame as input. Apply the formula to calculate daily returns. Use proper slicing and indexing to avoid having to loop over each value. Note that the return data frame must contain the same column labels and the same number of rows as the given data frame, which means if there are any missing or unknown values, replace them with 0. First, we make a copy of the data frame where we can save computed values. Dataframe.copy will help us with that. For the next part, let's consider this. Suppose we want daily returns for date at index t. Then we need to divide the value at index t by the value at index t-1 and subtract 1. We want to do that for all the dates, starting with index 1. Now let's code this. Here, df1 : picks all the rows from 1 till the end, and df:-1 picks all the rows from 0 till 1 less than the end. This operation cannot be done at index 0 since we do not have the price of the stock prior to this day. So we set the values at the 0th row to all zeros. Finally, we return this data frame. You must be wondering, why did we use .values attribute of one of the intermediate data frames? The reason is to access the underlying NumPy array. This is necessary because when given two data frames, pandas will try to match each row based on index when performing element-wise arithmetic operations. So all our effort in shifting the values by 1 will be lost if we do not use .values attribute. Okay, now let's run this. Here is what the daily returns look like compared to the original stock prices. As you can see, the original prices of SPY and XOM are quite different. However, since the daily returns are implicitly normalized, they show up at a comparable scale. Each daily return value is either positive or negative fraction relative to the previous day's value. This reveals that Exxon or ExxonMobil actually matches ups and downs of the SPY quite closely. There is another way to compute daily returns, this time directly using Pandas data frame. Here is how we can do it using Pandas data frame function shift. Note that we still have to replace the values at the 0th row with zeros. The reason for doing this is Pandas leaves these unknown values as nan by default. Now let's check the output. As you can see, the result is same as before.
One last important statistic on a stock that's important is called cumulative returns. So let's consider S&P 500, again back in 2012. Now in 2012, the S&P 500 started the year at $125 and it ended the year at $142. When you listen to the news, you hear things like, for the year 2012, S&P 500 gained 13.6%. That is cumulative return. You don't hear them say, over 2012, S&P 500 went from 125 to 142. So how do you calculate these cumulative returns? It's really easy. Here's the equation. The cumulative return for a particular day, T, is just today's price divided by the price at the beginning. So price of 0 is over here, and the price of any particular day, say would be here, and we can calculate the value like this. Now the cumulative return for the whole period is where T is this last day. So let's consider the example we've got here. To calculate the cumulative return for this whole year, it's the price at the end divided by the price at the beginning minus 1. Turns out 142 divided by 125 is 1.136. Minus 1 gives us 0.136, which is equal to 13.6%. So our cumulative return for the ETF SPY was 13.6%. We can calculate and chart cumulative returns just like we did earlier for daily returns, except now the plot is showing us the cumulative return, of course, instead of the daily return. Note that the shape of the chart is, the same as the price chart. It's just now it's normalized, and in fact, this equation is exactly our normalization equation. So that is how to calculate and plot cumulative returns. We're not going to have Dave show you how to do that. You're on your own there. Now that you know how to do daily returns, it shouldn't be too tough. Okay, that's it for this lesson. We'll see you again soon.
Historical financial data is, of course, essential for effective financial research. One reason people are attracted to finance as an area of research is because they believe the data is very well documented. In other words, all of the data is monitored and recorded by computer and saved for us to pore over later. It turns out, though, that there are many ways the data can be faulty. In this lesson, we're going to look at how missing data can occur and what we can do about it.
Now, as you might have guessed, the data isn't really pristine. So here's what people think financial data is like. They imagine that it's perfectly recorded minute by minute. The prices that are recorded are exactly right. The volume data is exactly right. But that's not the case. But that's not the only mistake people make about what they think the data is like. People assume there's no gaps in the data, that we have every single minute recorded, that data for stocks started since the beginning of time and they continue to the very last minute. The reality is that our data is an amalgamation created from many, many sources. For instance, for any particular stock, it may be traded on the New York Stock Exchange, at NASDAQ, at BATS, and over any particular minute during the day, it may trade at one price at New York Stock Exchange, another price at NASDAQ. The reality is that there's no single price for any stock at any particular time. And in fact, it's hard to say who's right. So the reality of the data that we get is that it's a combination from all these different sources, and different data providers will provide actually different numbers. And finally, one part of reality that's especially troublesome is not all stocks trade every day. Sometimes stocks come into existence and suddenly there's values for them, and before that there was no data. Sometimes stocks go out of existence and suddenly they quit existing and there's no data for them going forward. There's another kind of failure mode or missing data mode where a particular stock will be trading, data will be missing, suddenly it starts trading again. And these are the sorts of problems we're going to take a look at and find a way to solve in this lesson. Okay, let's take a look at some examples so we can see how prices are recorded over time. We'll start with SPY. This is showing a time series of that ETF over time. This is the downturn in 2008-2009. SPY represents the S&P 500. It's one of the most liquid and actively traded ETFs out there, and we typically use it as a reference, a time and date reference for other stocks, because we know if SPY was trading, the stock market was open, and we can use its time history as a reference in that regard. It goes all the way back to 1993. There are, of course, some stocks that go back further, all the way back to 1901 and so on, but most of what we're going to do, it's fine that we know it's been active since 1993. Now let's look at a couple more examples. We'll add Java, J-A-V-A, and as you can see, it was trading from the beginning here, but it, for some reason or another, abruptly stopped. Now what happened there? Well, you may remember that Sun Microsystems, which was trading under the ticker Java, was acquired by Oracle in 2010. And on that date, that ticker went away. So if you look at historical data for Java, you'll see that it ends at sometime in 2010. Something else that's interesting about this ticker Java is that before it was Sun Microsystems, it was actually Mr. Coffee. So if you look historically for data for Java, you'll find two different time series, one for when it traded as Mr. Coffee and another when it traded as Sun Microsystems, but it doesn't exist any longer. So imagine if you're processing this time series data and you arrive at this abrupt end for Java, what's going to happen? Well, in the data, you'll see NaN, meaning not a number, meaning there's no data there. And the focus of this lesson is what to do about that. Let's take a look at another example. Okay, we've added now an additional set of data, and as you can see, we named it fake, meaning this example we invented for the purpose of this discussion. Now, each of these symbols is available to you in the data that we provide you for the class. So you also will have this fake 1. Now, the data represented by fake 1 is fairly common, and we only invented it just so it would work out well on this chart that we're looking at. Anyways, what's going on with fake 1 is, as you can see, it didn't exist before this time. So instead of having, for instance, NaN values after a certain date, this fake 1 data is going to have NaN values before a certain date. So we'll have a different kind of problem trying to process that data. Now we'll look at one more example, and as you might have guessed, we named that fake 2. Now what's special about this one is it's got all of the different kinds of problems at once. So it didn't exist before this date, data was absent in between these two dates, and so on. This is not typical data for a very liquid, very large stock, for instance like Google or Apple. But indeed, data like this exists for thinly traded stocks. In other words, companies that don't have a high market capitalization, and they trade very little, if at all, occasionally. So we still have to be able to deal with data like this in our studies. And so let's focus on this fake 2 example. The question is, what do we do in situations like this where we don't have data between two separate dates. Now, you might think, gee, let's interpolate. And so we would estimate what a line is between those two dates and then fill in at each point an interpolated value. Why not do that? Well, the truth of the matter is, between these two dates, there was no trading. There really was no price for that data. But if we're going to do something like, for instance, compute a rolling average or a mean over that data, and there's nans there, that'll wipe out our entire calculation. So we can't leave it empty, but we shouldn't interpolate it either. So here's what we might do. One thing that we can do is we fill forward going from, we go over all the data, and when there's some missing data, we fill forward from the last previous known value. So for instance, if we were to do that here, we would get these values up until that date where it takes over there. We would fill forward here and fill forward here. Now notice there's a big gap between there, and there's a big gap here, but that realistically reflects what was going on with the data. Now the reason we do this instead of the interpolation is the following. Let's suppose we were looking for patterns in the data, and we had rolled back time and we were simulating history, and let's suppose for a moment we had this interpolation, and let's suppose we're right here in time and we're trying to figure out what's going to happen next. We're looking for patterns and so on. We're actually giving ourselves information about the future. We're observing that the price is going up. So if we were to make a calculation here, we would actually be peeking into the future, and that is not allowed. We do not want to do that. So we need to stick with only filling forward a last known price. If we do that, then we're not peeking into the future. So let's get rid of that ugly, nasty peeking into the future. Okay, so now we've actually filled in all our gaps, and we have continuous data from this start point all the way to the end. However, there still is missing data here at the beginning. And because we need some value here in order to calculate rolling averages or whatever sort of statistics we want to do, it's better to have some value here instead of not a number. And in this case, we fill backwards. So remember, if you're going to fill your data to resolve problems with gaps, fill forward first and fill backward second. That way you'll avoid, to the max extent possible, peeking into the future. Now we'll hand it over to Dave, and she's going to show you how to do this in code. Here's to you, Dave.
Thanks, Professor. I'll take it from here. So, hello everyone, and we will be using Panda's fillNan function to fill the missing data. So let's find a documentation of this function, and let's go to this site. So here it is. The link is included in the instructor notes. I encourage you to bookmark this site, so it gives the usage for any function at a glance, and it will help you a lot. So let's scroll down and let's search for a function using this small search box. Let's search for fillNan. Here it is. Data from fillNan function, and we'll be using this. Read and try to understand different options and how to call this fillNan function, and I'll be right back with a pop quiz. So here's a question for you. How would you call fillNan to fill forward missing values? Go ahead and type your answer in this box. So here's the answer. In order to fill forward missing values, we need to specify the method ffill. Note that the method value is a string, so it has to be enclosed in the quotes. So let's do some coding. To start with, let's use an example stock with missing values. We will be using fake2.csv, and this file is included in your data folder. So as usual, we will be reading the CSV into the data frame, and we will do some plotting. So now let's go and plot this data and see what turns up. So here's the graph. So for the given range of dates, you can notice that there is a gap in the beginning and also gap at multiple places in the middle. So now let's try to fix this. We only need to add a single statement to fill those gaps. As you must have read in the documentation, method ffill corresponds to forward filling and in place is equal to true will save all the changes in the same data frame. Try removing this and see what happens. Now let's plot and see how the graph looks now. So here's the graph. If you look closely, you will observe the forward filling effect. The stock prices retain their previous values throughout. However, note that the missing values at the beginning of the range have not been filled. Think about what you need to do to take care of that. Time for some coding quiz. Okay, here's some code to read in a data for multiple symbols during a specified period of time. If you go ahead and plot this, you see where we have data missing for Java, fake1 and fake2. Your task is to fill these gaps using the fillNav method, and yes, it can work for multiple stocks or in that case multiple columns of the data frame simultaneously. You can refer to the documentation and the previous example if you need a clue. Good luck! So here's the solution. To solve this, you need to use both forward and the backward fill. The key is to use forward fill first and then the backward fill to avoid peeping into the future as much as possible. Now let's see how the graph looks now. Here's the resulting graph. Note the effects of the forward filling and the backward filling in different segments of the missing data. That's all for now. Happy coding till I get back to you.
Daily returns are one of the most important factors for us to consider when looking at market statistics. But daily returns for a single stock just by themselves are not very informative. One of the most informative ways to consider daily returns is when we compare the returns of one stock with another.
We're going to use daily returns as a basis for the analysis in this lesson. And we build daily returns like we've seen before by starting with a price time series. And each point in this daily return chart is related to how much prices changed on that corresponding day. So for instance, this represents how much the price changed from this day to that day, about 1%. And of course we have that for each of the days in our history. Now looking at this data, this daily return data, it's not too revealing. It's hard to draw any sorts of interesting conclusions just by visually looking at this data from day to day. And so there's a number of interesting ways that we can look at that data. And that's what this lesson is all about. Those two ways are histograms and scatter plots. Let's start by taking a look at histograms. A histogram is a kind of bar chart where we plot the number of occurrences of each item versus the value. So the way we accomplish that is we split up the range of data into lots of little bins, and we count up how many times the data matches the range across that bin. So as an example, if you notice here, we've got several occurrences of this value, which is about the same, and those three occurrences are probably in, say, this bin. So when we go to plot the histogram overall, we would see a bar of the appropriate height here that represents how many times the data match that value. And of course, we have values in other bins, and so the bars in those bins would have various heights. And as you gather that data across all of time, a shape emerges of this histogram, and that provides a lot of information. So let's consider what that shape might look like. Suppose now that we've looked at, say, the S&P 500 over many years, and we've measured each day what the daily return is for the S&P 500, and we conduct a histogram and plot that histogram. So for each little bin, we have a bar there. What is the shape of this histogram going to look like? Do you think the bars, when we put them all together, will have a sort of flat shape, maybe a triangular shape, or something that's more like a bell curve? Check the box next to the histogram that you think is the best answer. The correct answer is bell curve. That's what many sort of distributions in nature, and if you can consider the stock market nature, it's not unusual that a histogram of daily returns ends up looking like a bell curve. Once we've got our histogram, there are a lot of statistics we can run on it to characterize it. For instance, of course, we might be interested in the mean. We might also be interested in the standard deviation, which is essentially, on average, how far do individual measurements deviate from the mean. Another very important measure is something called kurtosis. Kurtosis comes from a Greek word that means curved or arching. So what does kurtosis mean? Well, let me show you. Kurtosis tells us about the tails of the distribution. So the tails are the parts out here towards the ends. And if we assume that our distribution is similar to a Gaussian distribution or normal distribution, the measure of kurtosis tells us how much different our histogram is from that traditional Gaussian distribution. So in this case, we have what are called fat tails. I've got them over here and over here. What that means is that there are occasional and more frequent than would happen if we had a regular Gaussian distribution. There are frequently large excursions, more frequently than if this was a normal distribution. If you were to measure the kurtosis of this histogram, you would get a positive number, meaning that there are more occurrences out in these tails than would be expected if it were a normal distribution. If you measured a negative kurtosis, it would mean that there are many fewer occurrences out here in the tails than would be expected if it were a normal distribution. So we can plot our data in this sort of bar chart called a histogram. We can measure statistics on it like standard deviation, mean, and kurtosis. And remember the following about kurtosis. If we've got a positive kurtosis, that means we've got fat tails, like in this example. There's more occurrences outside in the tails than would normally happen with a Gaussian distribution. And if we've got a negative kurtosis, we've got skinny tails, meaning there's less out there. Now, I'm going to hand it over to Dave, and she's going to show you how to make this plot and calculate these numbers in Python.
I recently read a post on Humans of New York page, and this woman mentioned in an interview that programming is magic. It allows us to make things with words. Isn't that true? So let's create our own magic. Let's make histogram. Firstly, let's check out the ingredients needed to make histogram of daily returns. To calculate daily returns, we need to get stock prices first. To start with, we get stock prices for the SPY for a period of 3 years. Next step is to calculate daily return. This is similar to what we saw in lesson 4. Now we call this function and pass our data frame to it. We also plot the daily return value by passing the daily return data frame to our plot data function. This graph shows the prices of the SPY stock over 3 years. And this is the daily return graph for SPY. Now we have our base ready, so let's make our histogram. And after 5 lessons, you must have guessed that even this can be done in just one line. Here is our histogram. Professor explained the concept about bins. We did not mention the number of bins while plotting the histogram. The default number of bins is 10. If you look closely, you will observe 10 set of ranges. Can you see this? 1, 2, 3, 4 and so on. If you count, there would be 10. But as usual, Python is flexible and allows us to change the number of bins using the bin keyword. We inform the histogram function that we need 20 bins by passing a parameter bins and assigning it a value 20. Now let's check our changed histogram. Notice that the width of each bar has reduced and the number of bars has increased. If you read this graph, it would say that there are approximately 300 values which lie near 0. Next, we compute some statistics on the daily return. Starting with mean and standard deviation. We call the function mean and std on our data frame to get the values. Let's go ahead and check the mean and the standard deviation for the daily returns of the SPY stock. So we get the mean and the standard deviation. Happy with just knowing the mean and standard deviation value? But I am not. I want to see it on the plot, just like Professor did. So let's learn how to add mean and standard deviation line on plot. Matplotlib library has a function axvline. Looking at the substring vline, we can guess it will give vertical line. Let's check out its parameters. First we pass the mean value. Then, just for beautification and so that we can differentiate the mean line from the rest histogram, we add a color, which is white, make it a dash style line, and increase the line width to 2. Now let's check our output. So this is our mean, and this is how it is plotted on the histogram. Now let's go ahead and plot standard deviation. To plot the standard deviation line, it is similar to the mean, but as we want the standard deviation line on both sides of the mean, we plot it twice. One with the positive value and one with the negative value to show standard deviation line on either side of the mean. Ta-da! We have our standard deviation lines on our graph. To give the standard deviation a red color, I have just replaced the parameter color of white with red. Now I'm happy with the graph and I hope you too are. Let's move ahead to kurtosis. We can expect that data frame would have a function for calculating kurtosis as well. So that's it. This line will give you kurtosis of the daily returns. We get a positive value for the SPY stock, which means we have fat tails. Just for your information, you can also get bin counts using numpy.histogram function. Check instructor's notes for more information. Over to you, Professor.
A common practice in finance is to plot histograms of daily returns of different stocks together and look at them together and assess how they relate to one another. So here we've got a plot of an XYZ stock and SPY or S&P 500. Now take a look and see what differences you can see between them. Now to help out, I'll draw sort of what the underlying shape is looking like. Check which answer you think is most correct in terms of volatility and return for XYZ versus SPY. This is the correct answer. XYZ has a lower return and higher volatility than SPY. You can tell that if you look here at the mean of XYZ, you can see it's lower than the mean of SPY. You can see the shoulders are broad on XYZ, meaning it's got a larger standard deviation and therefore higher volatility. Dave will show you now how to plot histograms like this right next to one another in Python.
I'm back again, this time with a really small segment. We need to plot two histograms. So first, we read the values for two stocks. We get data for two stocks, which is SPY and XOM. We also go ahead and compute daily returns for each of the stock. Note that our daily return data frame will have daily return values for each of the stock prices. Now like before, we just call histogram function on the daily return data frame and let's see what happens. We keep the bins count to be 20. Now let's run this. Okay, so we got two subplots. But we go ahead one step and plot them on the same X and Y axis so that we can compare the histogram of SPY and XOM. To get two histograms on the same X and Y axis, we call the histogram function separately on each of the stock's daily return values. We also add the label parameter so that we can differentiate between the histogram of the SPY and XOM. Now let's run this. Here we go. We get two histograms of SPY and XOM on the same X and Y axis. Now you can compare the histogram and see that the tails of XOM is thin as compared to the SPY. That's it for this coding segment. I will be back soon. Over to you, Professor.
We're now going to take a look at another way to visualize the differences between daily returns of individual stocks. Let's get back again to our daily return chart. We've got S&P 500 here plotted already. And let's compare that to another stock, XYZ. Now note here that frequently XYZ moves in the same direction as SPY. but it also sometimes moves a little bit further, like in these sections here. We'll be able to visualize those differences in a scatter plot. So on a scatter plot, there are a number of individual points or dots, and each one represents something that happened on a particular day. So let's look at this particular day. On this day, SPY was positive, close to +1. So we'll look at +1 on SPY. And XYZ was about +1 as well, but a little bit larger. So that day would correspond to a point about there. Now, we look at each day one by one individually and populate all of our dots based on what happened each day. Another interesting day is this one, where SPY and XYZ were moving in different directions. So again, we had SPY in positive territory, but XYZ was in negative territory. So that would represent a dot about like that. Now, if we were to continue this process for very many days over a long period of time, for most stocks a trend appears, which is something like this, where you can sort of see there's a relationship here, maybe a linear relationship, and however, the dots are somewhat scattered. They don't form a perfect line. It is fairly common practice to take this set of data and fit a line to it using linear regression. Let's say we got a line something like that, and to look at the statistics of that linear fit. One property is the slope. When we fit a line, what's the slope of that line? Let's assume it turns out to be 1 for this particular stock and its relationship to the S&P 500. This slope in financial terminology is usually referred to as beta with this symbol, or just the word beta. And what beta means is how reactive is the stock to the market. So if beta is 1, and we have a slope here of 1, it means on average, when the market goes up 1%, that particular stock also goes up 1%. If we have, say, a higher number, say 2, that would mean that if the market were to go up 1%, we'd expect on average for that stock to go up 2%. There's another factor you can see here when you look at where that line intercepts the vertical axis. That is called alpha. And you've probably heard about alpha in investing circles, and what that means is that this stock is actually, on average, performing a little bit better than the S&P 500 every day if that number alpha is positive. If it's negative, it means on average it's returning a little bit less than the market overall. So that's how you can plot the data, fit a line to it, and measure a couple aspects of its performance with regard to the market or with regard to some other stock. Now, a mistake that a lot of people make is to confound slope and correlation. In other words, if they find that the slope of the line that fits the data is 1, that the data are correlated. And that's not true. The slope is just the slope. Correlation is a measure of how tightly do these individual points fit that line. So you could have a shallow slope, but the data tightly fitting that line, and thus a higher correlation. Or you could have a steeper line and the data fitting that line and a higher correlation. Correlation is just a measure of how tightly do those dots fit the line. And you can have a correlation from 0 to 1, 0 meaning the data is not correlated at all, and 1 meaning it's very highly correlated. Now we'll add a scatter plot for another stock, ABC, and again each one of these dots represents the daily return of SPY versus ABC, and we fit a line to it, and it turns out it's got a slope of 2. So now we're going to ask you a couple questions about it. Which of these statements is the most true about the relationship between ABC and XYZ in terms of beta and correlation? This is the correct answer. It's got higher beta because the slope is higher, and higher correlation because the dots are closer to the line that fits it. Now, Dave is going to show you how to create scatter plots and make these measurements in Python. Here's to you, Dave.
Thank you, Professor. So I am back with more Python and more graphs. This time, let's scatter some data. Let's learn how to build a scatter plot. We will compare scatter plot of SPY versus XOM and SPY versus gold. So let's read this data and compute daily returns as well. As usual, we call getData function with these symbols and also compute daily returns. Next, we first plot scatter plot for SPY versus XOM. Kind parameter of the plot function of the data frame will help us achieve this. So we mentioned we need a scatter plot, but since the data frame daily return has values for 3 stocks, we have to mention which should be our x-axis and which should be our y-axis. As we are plotting SPY versus XOM, we assign x attribute as SPY and y attribute as XOM. Ready to see the output? This is our SPY versus XOM. Now let's similarly plot SPY versus gold. Since we want gold on our y-axis, we just replace the y label from XOM to gold. So here are 2 scatter plots, SPY versus XOM and SPY versus gold. But we want to recreate the graph that Professor drew. So we fit a line to the scatter plots. For that, we need a help of another good friend of ours, which is NumPy. So let's import it. After importing the NumPy library, we are all set to fit a line to our scatter plot. So we have a set of points and we want a line which has an equation of degree 1. So we go ahead and fit a polynomial of degree 1. This is what polyfit function of the NumPy does. So let's use it. We will first do it for SPY and XOM. The polyfit function needs x coordinates and y coordinates to fit a line. For us, the x coordinates are the daily return values for SPY and the y coordinates are daily return values for the XOM. The 1 denotes the degree of our function. Calling this function will return 2 things. The first is the polynomial coefficient and the second is the intercept. Since we have a polynomial of degree 1, it would be of the form y is equal to mx plus b. So m is the coefficient and b is the intercept. We name them as beta and alpha, just as Professor explained. Now we finally plot these values. The idea for plotting the line is, for every value of x, that is SPY, we find a value of y using the line equation, which is mx plus b. This parameter denotes that we want a line plot with a color red. Now let's check our graph. Here is the fitted line. Now let's do it for gold so that we can compare them both. We also print the beta and the alpha values for each. Now let's compare the beta values, which shows how the stock moves with respect to SPY. You can see that the beta values for the XOM is greater as compared to that of gold, which means that XOM is more reactive to market as compared to gold. On the other hand, the alpha values denote how well it performed with respect to SPY. Numbers over here say that gold performed better. Let's cross-check. You can see the upward movement of the gold as compared to the SPY. One last thing is to find the correlation. Yet again, the data frame has a function CORR, which means correlation, and we can define which method to use. We use the method Pearson. It is the most commonly used method to calculate the correlation. There are other methods as well. Check the instructor's note for more detail. We get the output in the matrix format with correlation of each column with each other column. You can see that the SPY and the XOM are highly correlated. The value of the correlation for gold and SPY is very small. Let's check the graph. You can observe that the dots do not fit the line closely, and that's why the correlation value for the SPY versus gold is less as compared to SPY versus XOM. For more information on data frame scatter plot and polyfit, check the link in the instructor's notes.
As you have seen in this lesson, the distribution of daily returns for stocks and the market look very similar to a Gaussian. This property persists when we look at weekly, monthly, and annual returns as well. If they were really Gaussian, we'd say the returns were normally distributed. In many cases in financial research, we assume the returns are normally distributed, but this can be dangerous because it ignores kurtosis, or the probability in the tails. In the early 2000s, investment banks built bonds based on mortgages. They assumed that the distribution of returns for these mortgages was normally distributed. On that basis, they were able to show that these bonds had a very low probability of default. But they made two mistakes. First, they assumed that the return of each of these mortgages was independent, and two, that this return would be normally distributed. Both of these assumptions proved to be wrong, as massive numbers of homeowners defaulted on their mortgages. It was these defaults that precipitated the Great Recession of 2008. Up until this point, we've been computing statistics about individual stocks. We're going to shift now to computing statistics on portfolios. We're going to focus on some of the most important statistics that are used to evaluate the performance of portfolios and accordingly portfolio managers. We'll define a portfolio as an allocation of funds to a set of stocks. For the moment, we're going to follow a buy and hold strategy where we invest in a set of stocks with a certain allocation and then observe how things go moving forward. We'll assume the allocations sum to 1.0.
We want to be able to calculate the total value of a portfolio day by day by day. Once we have that information, then we can compute statistics on the overall portfolio. So let's start with an example. Assume we start with a portfolio value of $1 million, and we're going to take a look at that portfolio from the beginning of 2009 to the end of 2011. And our portfolio consists of these three symbols: S&P 500, Exxon, Google, and gold. And at the beginning, so at the beginning of 2009, we're going to allocate 0.4 or 40% of our portfolio to SPY, 40% to Exxon, 10% to Google, and 10% to gold. And we'll enter those positions at the beginning and hold them and step forward and see what the overall value of the portfolio is day by day. How do we calculate the total value of the portfolio day by day? Here's how to do it step by step. We start with our prices data frame. Remember the 4 columns with prices every day indexed by date. The first step is to normalize these prices. As we've done before, it's just the price values divided by the first row. So after we normalize, we have a new data frame normed, which is, as we said, all of the prices divided by the first row. So that's going to give us now this new data frame where the first row is all 1.0, and then it proceeds after that. And these are essentially cumulative returns starting from the start date. The next step is to multiply these normed values by the allocations to each of the equities. So we just multiply normed times our allocations, allocs, and that gives us a new data frame, alloct. Now, as you remember, our allocations were 0.4, 0.4, 0.1, 0.1. So when we do that multiplication, the first row is going to represent those numbers, and the data after the first row will be sized accordingly. Our next step is to multiply our alloc data frame times start val. And what that'll give us is, in this first row, the amount of cash allocated to each asset, and then going forward, it'll show us the value of that asset over time. So we've got now a new data frame, pos vals. What that means is position values, that at each day, that's how much that position is worth. So we started out, for instance, with 400,000 for the first one, 400,000 for the second one, 100,000, 100,000. But now as we go forward each day, it's as if we invested, say, 100,000 in this one, and it reflects how much it was worth each day after that. Now that we have the value each day for the individual assets, we can calculate the total value for the portfolio each day by summing across each day. So on the first day, for instance, the value of the portfolio is 400,000 plus 400,000 plus 100 plus 100,000. or 1 million. Now those values change, of course, as the stock prices change going forward, so each day is a little bit different. We can calculate the value for each of these days by taking the sum of pos vals, position vals, using axis equals 1. So that's telling Python to sum across each row like that. So that sums each day across into port val, which now reflects the value each day for our total portfolio. Let's recap now. We start with our prices. We normalize that to the first day, so the first row here is all ones. We multiply times our allocations, and that gives us now in each column the relative value of each of those assets over time. We multiply by our initial investment, and that causes now each row to be the real value of that investment each day over time, starting with our initial allocations. If we then sum each row, we get the value of the portfolio on each corresponding day. And that's it. That's how you calculate daily portfolio value. We showed a moment ago how to go from prices to port val, which is the daily total value of the portfolio. Now that we have port val, we can compute a number of important statistics on the portfolio and thus assess the portfolio and the investment style of whoever's managing that portfolio. An important first calculation is to compute daily returns. We've talked about how to do that before, so I won't go over it here. But an important observation is whenever you compute daily returns, the first value is always going to be 0. And that's because on the first day, of course, there's no change. So we want to exclude that value from any calculations we do across all daily returns. It's easy to accomplish this with a simple Python statement, which is just to replace daily returns with daily returns where we just include the second row forward. And boom, we're rid of that first 0. Now that we have this information, we can compute 4 key statistics that everybody wants to know about regarding the performance of a portfolio. They are cumulative return, average daily return, standard deviation of daily return, and Sharpe ratio. Cumulative return is just a measure of how much the value of the portfolio has gone up from the beginning to the end. So to calculate that, we take the last val, which is port val of -1, which is this one, divide it by the beginning, and subtract 1. Average daily return is just the average of these numbers, so we just take the mean. Very simple. And standard deviation of daily return, again, simple, just use the standard deviation function right there. Now, Sharpe ratio is a little bit more complex than these other ones, so we're going to spend a little bit more time diving into Sharpe ratio. The idea for Sharpe ratio is to consider our return or our rewards in the context of risk. So as we mentioned before, most finance folks consider risk to be standard deviation or volatility. So we're looking for a measure that essentially adjusts our return for that risk. So here are a couple of examples that I want you to think about, and we'll have a little quiz associated with it. But we have 3 example charts here where we're comparing 2 stocks against one another. So in this first one, we've got ABC and XYZ, and both of them have about the same volatility, except one returns a little bit more than the other. In this next question, question 2, they both return exactly the same amount, but one of them is more volatile than the other. And finally, we have, again, these 2 stocks. One, ABC returns 11%, XYZ returns 9%, but ABC is much more volatile than XYZ. So I want you to think about this and mark which portfolio or stock you think is better in each one of these examples. For number 1 here, ABC is the correct answer because its volatility is the same, but its total return is higher. So all else being equal, higher return is better. In this next one, the correct answer is XYZ. And the reason is XYZ had the same return as ABC, but it was less volatile. So, all else being equal, less volatility is better. Now, number 3 was a trick question. ABC has higher return, but it's offset by higher volatility. XYZ has lower return, but that's offset by lower volatility. So you don't really have enough information to make the choice here. You could sort of stand back and squint and look at it and tell you what your gut says, but we need a qualitative way to measure this, and that's what the Sharpe ratio is all about. Sharpe ratio is a metric that adjusts return for risk, and it enables us in a quantitative way to assess each of these example compared portfolios. So Sharpe ratio will show us, for instance, that in this case ABC is better because it has about the same volatility as XYZ but higher return. If it were to assess these two, even though they both have the same return, it'll say XYZ is better because it's got lower risk. And finally, in this case where these two are very close and it's hard for us as humans to determine which one is better, Sharpe ratio will give us a number that will help us determine between the two. So with regard to the numbers that Sharpe ratio ends up providing us, all else being equal, lower risk is better, higher return is better. Sharpe ratio also considers something called the risk-free rate of return. That's the interest rate you would get on your money if you put it in a risk-free asset like a bank account or a short-term treasury. The reason that it includes this number is we always need to consider, maybe this asset we've got isn't performing as well as the return I would get if I just put it in the bank. Now, lately, as of mid-2015, the risk-free rate of return is about 0. In other words, if you were to put your money in the bank or to buy very short-term treasury bonds, that's the interest rate they would pay you. And this is why lately folks have put so much money into the stock market, because you can't make money putting your money in the bank these days. The Sharpe ratio is named for William Sharpe, and he developed something called the Sharpe ratio that accounts for all of these. Now think about what the form of that equation would look like. Consider that you have these three factors: portfolio return, risk-free rate of return, and standard deviation of portfolio return, or volatility, or risk. How would you combine these three factors into a simple equation to create a metric that provides a measure of risk-adjusted return? In other words, like those examples we showed you before, all else being equal, higher return is better. All else being equal, lower volatility is better. Which of these three do you think is the best metric? This is the best answer. Here's why. First of all, observe we're dividing by volatility here on the bottom. So as things become more volatile, the ratio goes down. We've got return on portfolio here on the top. So as return goes up, the metric goes up. And finally, we subtract the risk-free return here. So as risk-free return increases, the value of our metric decreases, meaning that essentially we need to have a higher return on our portfolio than the risk-free metric in order to have a positive number here. And this is indeed the form of the Sharpe ratio. There are a few more details, but this is essentially the ratio devised by William Sharpe. Here's the equation for computing the Sharpe ratio as proposed by William Sharpe himself. It's the expected value of the return on the portfolio minus the risk-free rate of return divided by the standard deviation of that same difference. This is the ex-ante formulation, meaning, because we're using expected, it's a forward-looking measure of what the Sharpe ratio should be. Now, to calculate this in reality, we need to look back at those values. So, for instance, the expected value of this difference is just simply the mean of what that difference was over time. So to calculate this in Python using historical data, we just take the mean of daily returns minus the daily risk-free rate and divide that by the standard deviation of the daily returns minus the daily risk-free rate. Now, you may be wondering, what is this risk-free rate? Where can we get it? Traditionally, there are a few numbers that people use for this. One is LIBOR, or the London Interbank Offer Rate. Another is the interest rate on the 3-month Treasury bill. And finally, a value that people have been using a lot over the last few years is 0. 0 is a good approximation to the risk-free rate. Now, I've been presenting this as if this risk-free rate changes each day, and indeed, LIBOR changes each day, and 3-month T-bill changes a little bit each day. But there's a shortcut people use a lot that simplifies this equation significantly. And this shortcut makes sense because usually the risk-free rate is not given on a daily basis for instance, putting your money in a bank account or a certificate of deposit. Usually that's a percentage on an annual basis or a 6-month basis. So you can convert that annual amount into a daily amount using this simple trick. Let's suppose our risk-free rate is 10% per year, or 0.1. That means if we start at the beginning of the year with a value of 1.0, at the end of the year we have 1.1. So we add 1 here. So this is the total value of our asset at the end of the year. Now, what is the interest rate per day that would enable us to get to this value? It's a number that if we multiply it by itself each day for each day in the trading year, or 252 times, would arrive at this number. So here's how we do it. We take the 252nd root of that sum, believe it or not. That's pretty easy to do in Python actually, and subtract 1. And that is our daily risk-free rate. We are, in most cases in this class, just going to approximate the daily risk-free rate with 0 because that's what it's been for such a long time. Of course, it may be changing in the future, so keep this shortcut in mind. Now, suppose we want to use this value, which is fine. We would plug that in here and also plug it in here. So observe that if we plug a constant in here in this standard deviation calculation, we can just remove it because a set of values minus a constant when you calculate the standard deviation is just as if this were 0. Summing it all up, this is the equation we typically use for calculating Sharpe ratio using daily returns. We drop the daily risk-free rate from the standard deviation because we treat that as a constant. If our daily risk-free rate is greater than 0, then you need to plug it in here, but we can usually use a constant there as well. But wait, there's more. The Sharpe ratio for the same asset can vary widely depending on how frequently you sample it. So in other words, if you sample the prices every year and compute your Sharpe ratio based on yearly statistics, you'll get one number. If you sample monthly, you'll get a different number. If you sample daily, you'll get still another number. The original vision for the Sharpe ratio is that it's an annual measure. And so if we're sampling at frequencies other than annually, we need to add an adjustment factor to make it all work out. So if we have our original Sharpe ratio over here, we multiply it by an adjustment factor called K to get the annualized version. Now what is K? K is simply the square root of the number of samples per year. So for instance, if we're using daily data, there are 252 trading days per year, so K is the square root of 252. If we're, say, taking weekly samples, it'd be square root of 52. Important thing to keep in mind is the number in here is the rate at which we're sampling. So as an example, let's suppose we were trading for 85 days. Because we're sampling at a daily rate, we use this number for our K, square root of 252. Even though we only traded for 89 days, we use 252 here because we're sampling daily. It's the frequency at which we sample that affects this value for K. So recapping, if we sample the value of our portfolio monthly, k is square root of 12. If we do it weekly, it's square root of 52 because there's 52 weeks in a year. And if we sample daily, it's square root of 252. Bringing it all together, if we're using daily data, our Sharpe ratio is square root of 252, that's our k, times mean of our daily returns minus the daily risk-free rate, divided by standard deviation of daily returns. Assume we've been trading a strategy for 60 days now, and on average, our strategy returns 0.1% per day. Another word for this is 10 basis points. 1 basis point is a 1/100th of a percent. So 10 bips or basis points is 1/10 of a percent. Our daily return is on average 10 basis points. Our risk-free rate, which we'll assume is just a fixed number, is 2 basis points per day. And the standard deviation of our daily return is 10 bips or 10 basis points. What is the Sharpe ratio of this strategy? Correct answer is 12.7. That's a really eye-watering Sharpe ratio. Anyways, these numbers are just made up for example, so it's not surprising we might get an absurd number here. But here's how we calculate that. So remember, our Sharpe ratio is square root of 252 because that's how frequently we're sampling the data daily. 252 days in a year, square root of 252. A lot of people probably saw this 60 days of data and thought that it should be square root of 60. It's not correct. It's the frequency that you're sampling. Anyways, getting back to it, it's square root of 252 times the mean of portfolio return minus risk-free return divided by standard deviation of our daily return. So that becomes square root of 252 times 10 bips minus 2 bips divided by 10 bips. This just becomes 0.8, and multiply it all out, and you get 12.7.
Now you know how to compute daily portfolio values, and from there, important portfolio statistics. The main ones we're going to focus on are cumulative return, average daily return, standard deviation of daily return, or risk, and Sharpe ratio. These are the key factors most people focus on when evaluating the performance of a portfolio. The assignment associated with this lesson is for you to build a function that can calculate these values automatically. You've got what you need to build this, so have at it.
In this lesson, we're going to look at optimizers. Optimizers sound scary, but they're really cool and really fun. I'm going to show you all kinds of neat things you can do with optimizers. What is an optimizer? An optimizer is an algorithm that can do the following things. Optimizers can be used to find minimum values for functions. So say you have a function like f of x equals x squared plus x cubed plus 5 or something like that. An optimizer can find for what value of x is this overall function minimized. Another thing that optimizers can do is find the parameters for parameterized models from data. So we might have some data from some experiment, and we can use optimizers to find a polynomial fit to that data. And that's actually one thing we're going to learn in this lesson. Finally, we can use an optimizer to refine allocations to stocks in portfolios. So what does that mean? Well, that means, for instance, you can decide what percentage of funds should be allocated to each stock using an optimizer. How do we use an optimizer? It's really just as simple as 3 key steps. First thing you need to do is define a function that you want to minimize. As an example, you might use something like f of x is equal to x squared plus 0.5. You define that in Python, and then the minimizer will call this function many, many times as it tries to find the minimum value for x that causes this function overall to be smallest. You also need to start with an initial guess for x that you think might be close to the solution to the problem. If you don't really know, then you can choose a random value or just some standard value. But then the optimizer starts with that guess, and it repeatedly calls the function, tests different values, and narrows in on the solution. Finally, you call the optimizer with these parameters and stand back while it searches for the minimum. Let's take a look at this function. F of x is equal to x minus 1.5 squared plus 0.5. That function is a parabola that looks something like this. It's centered horizontally at 1.5, and its minima is here at 0.5. Now, the optimizer or the minimizer doesn't know that. We can tell it by looking at the equation, but the minimizer has to figure it out on its own. So let's suppose we tell it, hey, minimizer, why don't you start with a guess of 2.0 and see if you can figure out from there what it is. So the minimizer says, okay, I'll give it a go. And here's what it does. First thing it does is it checks the value at 2.0. It turns out that that's about 0.75. It then tests the value nearby, say here and here, and it finds out that, gee, this equation has a slope about like that at this point. Now it's trying to minimize, and so what it does is it marches downhill. It's called gradient descent, and it tries another value down along that slope. It gets a particular value here, tries another one, and so on, and eventually it narrows in and it discovers that 1.5 is the value for x at the minima, and the value of y there is 0.5. Now the example I gave you for sort of marching down this gradient descent is one method. There are many variations on that method that different kinds of minimizers use, and SciPy, the library that we're using, has many of those options, and you can choose different ones according to your taste. We're going to stick with one particular approach through our examples here, but you ought to experiment and try some of the other ones as well. Let's try that same example function now in Python code. So up here we have our normal imports. Here is where we define the function, and again we're simply using x minus 1.5 squared plus 0.5. Now within this function we're going to go ahead and print what the value is when we get called. It just is a little bit handier so that we can see what exactly is going on. But you don't have to have that, of course. And then we return y. Now this is going to be the function that we're going to ask SciPy, or in particular the optimizer, to minimize for us. And by the way, we've included this optimize package as SPO. So SciPy.optimize as SPO. This is our call now to the optimizer or the minimizer. Before we call it, we first set our guess value to be 2.0. And we're using the function minimize, so we call SPO.minimize. F, that's our function here. So we're saying, minimizer, please minimize, find the minimum for this function. XGuess is our guess. Method is we're directing minimize to use a particular minimizing algorithm. We'll talk a little bit about that a little bit later, but this is one of those particular algorithms that happens to work pretty nicely. We send it one more option here, disp, which is true, which means we just want it to be verbose about things that it discovers. Anyways, that's it. That calls the minimizer. The minimizer repeatedly calls our function and finds the minimum value. Then it prints out those results. Let's try a test run and see what happens. Remember, in our function that we wanted to minimize, we explicitly printed x and y. So here you can see each time it gets called, it prints these values out. And so the minimizer is repeatedly calling that function f, and it's printing these things out. So it gets called initially with an x of 2, and it discovers that the value is 0.75. then a value slightly greater than 2, a value slightly less than 2, and the minimizer very quickly converges on 1.5 as the answer. And here it prints out those values, finds the minima at 1.5 with a value of 0.5 there. So pretty efficient and effective discovery of the minimization. I added a few more lines of code here, which I'll highlight merely to plot the answer. So all the rest of the code is the same, but let's take a look now if we plot it as well. So same result as before, but nice plot with our minima identified right here. So that is how to code up a minimizer. It's really very easy and really powerful. Let's look at it a little bit further. Now that you know how minimizers or optimizers work, think a little bit about what might be hard for them to solve. So I'm going to show you 4 example function shapes, and I want you to consider whether these would be hard or easy for the minimizer to solve. Here are 4 function shapes to look at. If you think that one would be hard for the minimizer we just talked about, check the box next to it and tell us why. Type out a reason in the text box. All right, have at it. Most of these are hard. This one's hard, this one's hard, and this one. And let me explain why. This one is hard because of this flat area here and here. Suppose the minimizer tested this point here and then tried on either side. It wouldn't be able to find any gradient to follow, so it wouldn't know which direction to go. This one is difficult for at least 2 reasons. One is it has several local minima that aren't necessarily the global minima, so it might iterate and find, say, this as a minima, but notice that actually there's these other 2 that are actually smaller. And then if these 2 have exactly the same value, it turns out we have 2 global minima. So those sorts of conditions are tough for these minimizers to solve. This one is challenging, A, because of this flat area, but also because of this discontinuity. So 4 examples, 3 of them would be hard for our minimizer to solve. Now, I'm not saying that these are not solvable by optimizers. In fact, there are optimizers that can solve these problems with varying degrees of success. And they're likely to find a minima, just not guaranteed to find the minima. While we're on the topic of problems that are easy or hard for optimizers to solve, let's talk for a moment about a particular class of problems that are indeed the most easy for these types of algorithms to solve. And those are called convex problems. Here's the formal definition of a convex function. I'm going to read it to you from Wikipedia, and then I'll show you what it means on these graphs here. A real-valued function f of x defined on an interval is called convex if the line segment between any 2 points on the graph of the function lies above the graph. Okay, a lot of words there. Let me show you what that means more easily. First step, choose 2 points and draw a line between them. Now for each of these lines, if the line is above the graph everywhere between those 2 points, then the function is convex between those points. So for this function, yes, it's convex because the line is above the graph everywhere. In fact, any 2 points you choose on this graph will have that property. So this function is convex everywhere, at least where we're looking at it. Here, notice that this part of the graph lies above the line. So this is non-convex. Similarly, this one, we've got this region here that lies above the line. So this one is also non-convex. And this one is, of course, convex. So a couple things to observe here, some properties that emerge. One is, in order for the function to be convex, it has to have only one local minima, and in other words, that local minima is the global minima. This one fails for that reason. We also can't have any flat regions that essentially don't have any slope downward. Now, if the function you're trying to find a minima for is convex, then these algorithms will find the minima quickly and easily. But again, there are algorithms that can still find the minima for more complicated examples like these. But they require a little bit of randomness, and they aren't necessarily guaranteed to find the global minima. So far, we've been looking at functions that just have one dimension in x. So for instance, the parabola that we looked at. It's just as easy for these optimizers to work in multiple dimensions. Here's an example of a function that has 2 dimensions in x. It still has its y result. But the minimizers can solve these problems with gradient descent just as easily. So instead of just one dimension, we can have 1, 2, 3, 4, as many as we'd like. Now we're going to do something really cool. I'm going to show you how to build a parameterized model from data. What do I mean by parameterized model? This is an example of a parameterized model that you're probably familiar with from algebra. It's a function of x, and it has these 2 parameters, m and b. In fact, as you're probably aware, this is the equation of a line. So m and b are the parameters of that line. Now for convenience in our code, instead of using m and b, I'm going to use c0 and c1 just to be consistent. Let me motivate this with an example. Let's suppose we have some data from an experiment. Now this can work for many sorts of experiments, but for now, let's assume we've taken some measurements of humidity, and we've observed on those particular days we measure the humidity, how much it rains. So each dot here represents one day and one sample of data. So on this date, it was this humid, and it rained that much. Now we probably have lots more data, one for each day. When we look at this data, we see there's a kind of relationship here. And our intuition is maybe that it could be fitted by a line. Just sort of by eyeballing it, looks like the line might look about like that. And so our parameters here, coefficient 0 is equivalent to the slope here, and coefficient 1 is the y-intercept. So our task is to find c sub 0 and c sub 1 that provide the equation for this line that best fits the data. The question here is, how do we reframe this problem so that it makes sense for our minimizer? What is it we're trying to minimize? So restating the problem, suppose we have our original data points here, and we're trying to discover the equation of a line that best fits those points. Suppose this blue line is a candidate line, and we want to evaluate it. Is this good or bad? So the equation for that line is our first coefficient times x plus the second coefficient. And what the minimizer is going to do is it's going to vary this c0 and c1 to try and minimize something. And so we have to come up with an equation that gets lower in value as this line better fits the data. What should we use for that equation? So here's one step towards solving this problem. We can take a look at each one of our original data points and observe how far away it is from this line that we're evaluating. Let's call each of these distances e. So e sub 0 is that one, e sub 1 is that one. Can we come up with an equation in terms of e, or error, that gets us to this solution? Here's a quiz to get you thinking about that. So again, e is the error at each point. In other words, this is our original data point. This is the line that we're hypothesizing might be a good solution. and we can test how far off our model or our line is at each one of these points and measure that as E. So which of these formulae might be a good overall error measure? There could be more than one. So these two are reasonable answers. The reason that this one is not a good answer is because some of these E's might be negative. In other words, this one is negative, these two are positive, but you could end up with a negative error if you just added them up. You can fix that by adding absolute value or by squaring it. This measure here is one of the more famous one. Of course, it's squared error. Let's step through this now with an example of how a minimizer would try to find the coefficients of a line that best fits this data. So keep in mind that we have to give the minimizer an equation that it has to minimize. And what we're going to give it is that error metric. In fact, we'll use squared error. So we might guess an initial C0 and C1, and that would be a line like this. And we would give that to the minimizer and let it go. So it would measure the error with this particular line. It would fiddle with these values a little bit and see how much the error changed. Try a new set of values, see how that works. And eventually it's going to iterate, and eventually it's going to settle on what it thinks is the best solution. So key points here are that we express the problem for the minimizer as a minimization problem, and we give it the equation to minimize as the error. And then what it finds now instead of x is it finds the values for these coefficients. So let me show you how to do that now in code. Now we'll look at some example code that can fit a line to data that's given. Remember, we're using a optimizer to do this, and first thing we have to do is describe for the optimizer what is the function it's trying to minimize. So we'll call this function error, and it takes two parameters, line and data. Line is just two coefficients, C0 and C1, and data is just a list of data, of course. We've got some nice comments here that explain it, but really our error is expressed simply in this single equation. We have the value of the actual data at each point here minus the estimate that the line we're currently looking at would give at that same point. So we use the 0 coefficient and the 1 coefficient times the x value of the data at that point. So we take those differences and square it, and that's our error function, and that's what we're trying to minimize. We've added some code now to illustrate how to use the minimizer to find the equation of a line. We start with our original line that the minimizer doesn't know. So it's our secret, but we're testing it to see if the minimizer can discover the equation of this line. Here's the equation for our line. It's just a two-element array. It'll have a slope of 4, so coefficient 0 is 4, and a y-intercept of 2, so coefficient 1 of 2. Here we generate x and y values. Again, keep in mind our minimizer doesn't know these, but we're just generating them so we can look at them, and we're plotting it for looking at it later. We take that original line and we use from NumPy the random function to add some noise to it. So at each point along the x-axis where we have data, we add some noise. So now we've got our original line plus some noise, and we're going to challenge our minimizer to find the equation for that original line even though there's noise. We wrote a separate function, fitLine, that takes the data and the error function we defined and finds the equation for that line. Here's fitLine that does that for us. Two parameters, the data. So remember, this is noisy data that is approximately a line. In other words, we took our original line and added noise to it. and the error function, or the function we're trying to minimize. We have some nice comments here that tell us what those are. But now we just follow the steps like we've talked about before. We start with an initial guess. Here our initial guess is a slope of 0 and a mean of the rest of the data as our y-intercept. It could be anything really, but that is a reasonable guess. We plot the initial guess so we have something to look at, and I'll show you that later. But here really is the meat of the function. You've seen it before. So we call our minimize function with the error function. In other words, this is the function we're trying to minimize, our initial guess. And this is a parameter you haven't seen before, but this is a way by which we can pass the data to our error function. This is the method that we're going to use. And finally, although it goes off the end here, we'll set display to true, which will mean we'll get to see any information as it goes along. So that's it. I mean, really, the key here for this is this minimize call right here, and then it returns the result. So let's run it and see what we get. There was some additional code that I skipped over that generated this plot. You can look at that on your own, of course. Okay, let's take a look. Our original line is this blue line. Of course, the minimizer doesn't know anything about that. These green dots are our noisy data, where we just added noise values to the blue line. Now, we're asking our optimizer, okay, find the equation of the line that best fits this data, and the metric you're trying to minimize is error. So we passed it an initial guess here of this purple line and this data. So that's all it knows right now, is this initial guess of a purple line and this data. And then it iterates and tries different slopes and different y-intercepts until finally it converges to this red line, and that's the solution. And I think it looks pretty decent. We can check it here. So if you look in the code, you'll see that our real line had a slope of 4 and a y-intercept of 0.5. So it got 4.17 and 0.64. Not exactly, but if you look at the data, you can see that it's pretty hard to know exactly what the underlying line would look like. So I think our equation solver did a pretty good job. We can fit even more complicated functions to data like this. I'm going to show you the code of how to do that in just a moment, but I wanted to start with sort of the result and then go back into the code and show you how we did it. So our original polynomial is a blue line. It's under here. You can't quite see it. And the noisy data are the green dots there. This purple line is our initial guess, and the fitted polynomial, the red line here, fits the original pretty closely. So let me show you a little more detail. Here is output from our program. This is our original polynomial. It prints it in kind of a weird way. Our original polynomial is 1.5x to the 4th minus 10x to the 3rd minus 5x squared, and so on. And down here are the results of our optimization. So here's what we got. Instead of 1.5 for the 4th power, we got 1.6. Instead of negative 10 for the 3rd power, we got negative 10.5, and so on. But overall, pretty close. And as you can see by that chart I just showed you, very nice fitting. Let's look now at how we did that in code. The code here for a higher degree polynomial is very similar to what we had for the line. Again, there's an error function we're trying to minimize, and we take in the coefficients for the polynomial and the actual data. And our error function is computed here. Again, it's a sum of the difference between the actual data and the polynomial value squared. We take the sum of all those values, and that's our error. So again, very similar to what we did for the line. Here's our function that finds the coefficients of the polynomial. It has just a few parameters, the data that we're trying to fit, our error function, in other words, how do we measure error and what are we trying to minimize, and the degree of the polynomial. We create an initial guess, in other words, what do we think the values of the coefficients are, and what we're doing here is we're just setting them all to be 1s. We plot that, and then we call our minimizer, just like before. We have to tell it what's the error function we're trying to minimize, what's our initial guess. We have to pass along the data, which then gets passed to the error function. And again, this method SLSQP. And finally, you can't see it, it's off to the side there, but same options, essentially the verbose options. And that's it. That's how we use Python to create a model based on data.
Let's review what we learned. I showed you how to use a minimizer to find x such that f of x is minimized. I showed you how to minimize in multiple dimensions and how to use a minimizer to build a parameterized model. Where can you go from here? There are a number of ways you can carry this forward. You can use functions besides polynomials, you can model stock prices, or you can optimize a portfolio. Your final project in this mini course is to create a portfolio optimizer. That might sound like a tough problem, but you've already got the tools to do it. In this short lesson, we're going to lay the groundwork to help you know what portfolio optimization is and how to build one. First, what is portfolio optimization? Given a set of assets and a time period, find an allocation of funds to assets that maximizes performance. What is performance? We could choose from a number of metrics, including cumulative return, volatility or risk, and risk-adjusted return, which is Sharpe ratio. You can use any criteria you like, but for this assignment, we're going to focus on Sharpe ratio. Now, let me show you how to use a minimizer to optimize a portfolio.
As an example, consider this portfolio where we have Google, Apple, Gold, and Exxon from the beginning of 2010 to the end of 2010. This is what the performance of that portfolio would look like in the blue line if we had an equal allocation to each asset. So we gave 25% to each of those stocks at the beginning, and then we observed at the end the total performance. And we include here a chart for S&P 500 for comparison. Now this is a unoptimized portfolio. Here's what it would look like if we optimized for Sharpe ratio. Look at that. Look how much higher performance we get compared to our benchmark S&P 500. And observe over here the allocations to the assets. 60% goes to Gold, 40% to Apple, and none to Google or Exxon. Now, one thing to emphasize here is this is looking back in time. So we're looking back historically what happened in 2010 and observing at the beginning of 2010, if we knew what we knew now, how should we best allocate? So there's a question as to how much this can help our portfolio going forward. And I'll give you that answer ahead of time. Indeed, when we optimize for Sharpe ratio, hold that portfolio, rebalance, in other words, re-optimize for Sharpe ratio and continue that month by month, we very often, most frequently see that that improves the performance of the portfolio versus just an equal allocation. But I do want to observe that this is computing back in time, so yes, of course, we can find a better portfolio, but indeed it helps going forward as well. Suppose I were to give you the following problem. Take these 4 stocks, and over a particular time period, I want you to find the optimal allocation to those 4 stocks. I might ask you to find the optimal allocation that maximizes cumulative return, minimizes volatility, or maximizes Sharpe ratio. Which of these optimizers would be the easiest to write, and why? The answer is it would be easiest to write an optimizer that optimizes for cumulative return, because all you have to do is find the single stock that maximized return over that time period. If you're going to optimize for minimum volatility or Sharpe ratio, you actually have to evaluate various combinations of those stocks. In this case, the allocation would just be 100% to the highest returning stock. We're going to focus here on optimizing for Sharpe ratio. So solving that problem is not trivial, but it's not too hard either. What we need to do is frame the portfolio optimization problem as a minimization problem, and then we can solve it using the tools you have already. As you recall, in order to use a optimizer that minimizes, we have to do three things. First, we have to provide a function to minimize f of x that takes in x, 2, an initial guess for that x, and 3, call the optimizer and let it run. Now, in this case, x are the allocations that we're looking for. And we want the optimizer to try different allocations in order to discover the best set of allocations that optimizes this function. Well, what is that function exactly? We said just a moment ago that we want to optimize for Sharpe ratio. So, is this just Sharpe ratio? Well, not exactly, because what the minimizer will do in this case is try to find the smallest Sharpe ratio. So it'll find allocations that minimize that. And we want, of course, the largest Sharpe ratio because larger Sharpe ratios are better. That's easy to fix. All we do is multiply this by -1. So all that we want our optimizer to do is optimize for a negative Sharpe ratio, and that'll find the best allocation or the best value for x to solve this problem. And remember, x can have multiple dimensions, so each dimension of x here is an allocation to each of the stocks. So if we're trying to solve for a portfolio of 4 stocks, x will have 4 dimensions, and the value for each of those dimensions is the percentage of funds to allocate to each of those stocks. There's 2 more things you need to know about before you start optimizing portfolios. One of them will help your optimization run faster, and the other is essential for you to get the right answer. Let's start with the faster thing first. The first thing you can do is you can tell the optimizer that it should only look at certain ranges for x. In other words, for this problem, for each of the various allocations, it's only worth looking at values between 0 and 1. In other words, a value of 2 would indicate 200% of your fund is in a particular asset, and that's not possible. It's only feasible to have 0% to 100% or 0 to 1 in each of these assets. So you can tell the optimizer only focus on values between 0 and 1 for each of the dimensions of x. And if you do that, the optimizer can run much more quickly because it knows not to look at other values of x outside those bounds. It limits the search area significantly. Another thing you can do with the optimizers in NumPy are provide constraints. Constraints are properties of the values of x that must be true. As an example, we want the sum of our allocations to add up to 1. So let's say, for example, we're trying to optimize for a portfolio of 4 holdings. So we have x0, x1, x2, x3. We want the sum of the absolute values of those to be equal to 1.0. In other words, our total allocation should add up to 100%. The optimizers we use in this class have the ability for you to express that, and that guarantees that at the end, when it finds out the values for x, you end up with a total of 100% allocated to the various assets. Now, we're going to show you how to do these 2 things in the assignment text itself because the syntax is a little bit tricky and we want to convey to you exactly how to do that. So we look forward to seeing you solve this problem, and good luck on your final project.